everyone. Just in case the silence seems uncomfortable, we'll be starting in a minute or two. Just waiting for the clock to tick by to 9:30. So, good morning, everyone. It's about 9:30 and people are still trickling in. I see the list of participants sort of growing. So maybe we'll wait just a minute or so before we kick off our inaugural session. Okay, let's get going. So good morning, dear colleagues, or whatever is the appropriate greeting for your time zone. Yeah. On behalf of the Astronomical Society of India, I extend to you all a very warm welcome to join us for this 39th meeting of the Society. This meeting is being hosted jointly by ICTS-TIFR in Bangalore, ISER Mohali, IIT Indore, and IUCAA in Pune. And we thank the participants of this meeting for their enthusiasm. This time we have 606 registered participants as of this morning. And this is at least 50% more than the largest number, or maybe not at least, but almost 50% more than the largest number we have ever had registered for us. And this time we also have our participants distributed all across the globe from the west coast of the US to the east coast of Australia. And many people have worked hard to put this meeting together, and we sincerely hope that you will find it interesting and useful and perhaps even invigorating to learn about interesting work being presented here. Make use of this opportunity to interact with colleagues who you have perhaps known for a while and maybe some others who you have never met. And I hope and wish that you're healthy and comfortable wherever you are and that you will make the most of the opportunity presented by this meeting. And we have a very short and sort of to the point inauguration ceremony. I don't have much more to say except to now invite Professor G.C. Anupama, the President of the Astronomical Society of India, to join me in welcoming you and to deliver the presidential address. So over to you, Anupama.
Sorry, yeah, thanks for pointing out I was muted. Yeah. So good morning, everybody, and welcome to this virtual meeting of the ASI. We would have certainly liked to have had this meeting in person, but unfortunately the present time has not allowed us. But there is an upside to this. We have a larger number of participation, and I hope the deliberations will also be interesting. So once again, I join Divya in welcoming all of you for this meeting. And as Divya mentioned, the VOC, as we call it, or the Virtual Organizing Committee, has put in a lot of effort to make this meeting a success, and I am sure we'll have a very fruitful meeting. So let me go on to my presentation. Um, I'll just share my screen. Okay, so what I would like to talk about is a vision for astronomy and astrophysics in the coming decade or so, and what is what should be the ASI's perspective on this. So interestingly, ASI is in its 50th year, will be completing 50 years next year in 2022. And this coincides with the 50th year celebrations of the Department of Science and Technology, and also one of the oldest astronomy institutes in the country, that is the Indian Institute of Astrophysics. Both these organizations are completing 50 years in this year, and the ASI will be completing its 50th year next year. So, so far the scientific activities for society have mostly been the annual meetings and the publication of the journal, the bulletin, which has now been merged with the Journal of Astrophysics and Astronomy, and the JA is now jointly published by ASI and the Indian Academy of Sciences, Bangalore. In the recent times, the outreach and the education activities have been more active. We have a very active public outreach and education committee. Another recent activity that the ASI has been involved in is the gender equity and raising the awareness of a gender balance within the community. So what is now proposed is to have a vision document for the growth and development of astronomy and astrophysics in India, which will address issues such as the science, of course, and then the facilities, the human resource development, outreach, and education. Now, the government of India has been going through this exercise of having a science, technology, and innovation policy. We had circulated the draft, which was open for public viewing and for feedback. We had circulated the draft to all the ASI members. As a part of this policy exercise of the government of India, they have this mega science vision document, which is getting ready, which they call as a Mega Science Vision 2035. So I quote here from the website of the Office of the Principal Scientific Advisor to the Government of India on what this Mega Science Vision 2035 exercise is all about. What it says is that the next Mega Science Vision, abbreviated as MSV 2035, exercise has been undertaken by the Office of the Principal Scientific Advisor to the Government of India. The support to these projects has now become necessary in fields of research due to the need for experimentation, collection, and analysis of data on large scale. The year 2035 has been chosen, keeping in view the timelines of similar exercises that are undertaken elsewhere in the world, and the expected lifetime of the utilization of major global facilities in which India is involved in the present time. The MSV 2035 exercise has begun in the right earnest and will result in a roadmap document in the said areas of the widespread national stakeholder consultations. So what is a mega science project? As once again defined by the PSO's office, a mega science project should appeal to the scientific curiosity of the researcher in search of answers to some of the most important questions facing the world of science. It should be of interest to a large scientific community from various research groups within the country and outside. Mega science projects would be very large in terms of outlays or the complexities involved. And therefore, a user group, institution, or even individual countries would need to join hands with each other, similarly interested groups. Implementation of such projects would involve multi-institutional teams and also including possible international collaborations. A mega project has large outlays. It's large in terms of complexity, collaborative in nature with teams and groups from several institutions, nationally or internationally. So to give a background on the mega science projects, the government of India has been supporting mega science projects for a fairly long time. Some of the first participants in the mega science projects have been in the areas of high energy and nuclear physics since the 1960s. And initially, these were through the participation of individual scientists or institutions. With the CERN India agreement in 1991, followed by the CERN India protocol in 1996, which actually enabled the Indian participation in the construction of the Large Hadron Collider, the government entered into a formal involvement in these mega science projects. And the choice of the projects have been through bottom-up national consultations and through national vision meetings, which have been organized since the 9th plan period. These vision documents have prioritized the list of projects. They've also enabled smaller programs. And, but so far it has mostly been in the area of the high energy and nuclear physics, predominantly in this area. But as far as astronomy is concerned, in their own way, we can treat the project suggest the development of the Vainu Bappu telescope in the mid-1980s, the GMRT, these kind of projects can be considered as mega projects. And in recent times, we have had the AstroSat, the Aditya L1 is another ongoing project, and the 3.6 meter Jassal optical telescopes. So these can also be considered mega science projects in a certain sense. It was in the 11th five-year plan that these activities acquired a separate identity as mega science projects. And the current mega science projects that India is involved in, with a few exceptions, were all identified during the 11th plan period. Within astronomy, we all know that India is participating in the 30-meter telescope, the Square Kilometer Array, and the LIGO India projects. But as I mentioned earlier, astronomy was never a subject as a part of this exercise of the vision document. And it is for the first time that astronomy features in this exercise. And it's just right that the Astronomical Society of India plays a major role in this exercise. So what is MSV 2035 and what is the requirement for this document? It is to map the emerging knowledge contours in the field globally, also map the national scientific and technological strengths, and laid down a prioritized list of mega projects which India should take up as a nation, either nationally or internationally. Should be prepared after extensive and intensive bottom-up consultations nationally or, if necessary, even internationally. It should serve a useful purpose, and the list of projects should be within realistic expectations of the resource availability till 2035. The target group for this document would be the national funding agencies, the general public, national and international policy organizations, and various such interested communities. So why is this year 2035 chosen? This is because some of the currently operational mega facilities are expected to run till 2035, or rather the projects are expected to run till 2035. It takes 10 to 12 years to plan and build such facilities. But of course, this does not mean that the next vision exercise will be only in 2035. This exercise, as I understand, is held roughly every 5 to 6 years, where these plans are updated or modified. But what is also important to keep in mind is that, does the inclusion of a particular project in the report guarantee funding by the funding agencies? It's no. But what it will certainly help is that having a project in this list by the community will act as a guide for the funding agencies. Of course, for every project, a separate project report will have to be submitted, and one will have to go through all the requirements for the project approval and funding. So what should be the content of this draft report, which is now being expected of us? Of course, there will be a very brief on the background of this MSV 2035, and it will contain the emerging scientific technological frontiers in the field, the most outstanding scientific questions globally, the status of efforts being made globally to answer these questions, address the global plans till 2035, provide the status of national research and development, the strength of the community, both number-wise and intellectual strength-wise. Also provide a growth outlook for the community in India with 2020 as the baseline. The report will contain a priority list of projects in which India should get involved globally or should take up nationally in specified investment bands. There are some bands which are provided as an example, but this is not necessarily sacrosanct. It should also include smaller feeder enabling facilities and educational programs. Should include the current projects that we are already committed to, like the TMT, the SKA, the LIGO India, and any other such project. Should include future projects and projects that have been proposed already, like the National Large Solar Telescope, the National Large Optical Infrared Telescope, the proposal to have a sub-millimeter facility in the country, and the proposal to participate in the CTA, the international project. It's also important that we point out what we shall lose as a nation if we do not take up participation in these mega projects. The report should also contain the expected deliverables with 2020 as a baseline, with suggestions for implementation. And of course, one should not forget that accountability is extremely important. We should also look at industry involvement and how we are going to enhance the industry involvement. And there should be suggestions for public outreach and education. So some of the issues that certainly needs to be debated are how many mega projects should we participate in? There are several considerations that have been suggested, and these are the number of projects in which a single scientist should be involved in at any given time, and the expenditure on the projects which should also lead to a reasonable investment per scientist per year. We should be looking at the global competitiveness, but we should also see that, should we aim to be globally competitive in all the facets of the field, particularly given the available manpower strength we have in the country? Should we be prioritizing the national projects in those international projects which actually aid in building national projects? Can we think of some projects in niche and gap areas to be taken up nationally on our own or with international participation on the Indian soil? So what we need to be looking at is that we should be looking at logical and scientific steps for our facilities that can be taken up by us or in collaboration with the other nations. The main thing is that the goal should be to produce internationally competitive science or develop crucial technologies of national importance. We should also be looking at the steps required to build the ecosystem. So we should have a mix of international and national projects with consciously laid down interconnects. We should look at having a very highly thriving postdoctoral programs and doctoral programs, graduate training programs like training schools which match the demand and the supply. This is extremely crucial. Make a special effort to draw engineering students and faculty to such mega projects. Launch graduate level courses in selected universities and institutions. Have schools, workshops, and training programs. Have an extremely effective public outreach. You should also be looking at the metrics for the achievements. There are a few of these metrics which are listed. As far as the research and the development activity is concerned, we should be looking at the number and spread of the institutions involved. The more number and the spread across the country is always better. Have a larger number of scientists involved. So participation in these projects should increase the number of Indian scientists in the top 100 scientists internationally. Although it's definitely a matter of debate on what you mean by this and how you kind of treat this. The participation in these projects should lead to number of papers with distinct and important Indian contributions. The number of Indian PhDs should increase, and we should be having more number of Indian PhDs finding subsequent placement in top global institutions. From the technical aspect, we should be obviously having a large number of engineers and technologists involved. We should be looking at very active industries participating. And some of these other things like what should be the benefit to the Indian industries, and looking at the technology transfers to the Indian industries is something in line with the present policies of the government. And we should also be looking at the number of international projects that will be benefited from crucial know-hows and technology sourced from other international mega projects. So this is an exercise. The MSV 2035 is an exercise which has been initiated by the Office of the Principal Scientific Advisor to the Government of India. There have been similar other exercises. ISRO has had an exercise looking at the future space missions, particularly of relevance to astronomy and astrophysics. And this has had some suggestions by the astronomy community. I've just listed out a few of the suggestions. These are for having X-ray missions, particularly looking at having X-ray polarimeters, X-ray spectrometers, and fast timing X-ray instruments. In the UV missions, a spectroscopic survey mission has been proposed, a UV polarimetry has been proposed. We already have heard in the workshop a couple of days back about the INSIST project, which has got the seed funding. And last year, we heard about the Daksha project, which has also got some seed funding. So these are some of the future space missions that have been looked at. So what should ASI be doing? Now, regarding the MSV 2035, a drafting committee has been formed consisting of several members of the Astronomical Society of India, and that is looking into these various aspects of the report. ISRO has already had its vision document. So what should be ASI's vision document? It should actually be a superset of MSV 2035 and the space missions documents. We should also be looking at areas that have not been covered by these two documents, particularly small-scale projects and short-term projects. We should be looking at training and capacity building programs, the human resource development, most importantly, including steps to improve the gender balance, education and outreach, industry participation, synergy with allied areas and projects, and of course with several of the issues mentioned earlier to be debated. So obviously all this requires a very strong community participation. With respect to MSV 2035, a questionnaire has already been circulated to all the members of ASI and also within several astronomy institutes and departments. We have been getting responses and we expect the more responses to be coming soon. Once the report has been drafted, it will once again be shared with the community for their response before finalizing the draft to be submitted to the PSA's office. Dr. Sri Anand from IUCAA is the nodal scientist for this entire activity. And Shomak Rai Chaudhary and Anupama Subramaniam, the directors of IUCAA and IAA, are the chair and the co-chairs for this entire exercise. So for the vision ASI, we will be conducting a similar exercise of having the community participation. A vision document working group will be formed to draft the final document. And this will be one of the main activities that the ASI is going to take up during its 50th year. So I request an active participation by all the stakeholders in these exercises. So with these, I'll come to the end of my presentation. I would like to acknowledge Dr. Praveer Asthana, who is the National Coordinator for the Mega Science and Deep Technology Projects from the Office of PSA, for his permission to use contents from his presentation on MSV 2035. Thank you.
Thank you so much, Anupama, for a very apt and very timely topic which she picked up for her presidential address, the ASI vision document, and an opportunity to feed into relevant activities which are happening in the country in terms of the MSV 2035 and the ISRO vision document which has recently been submitted. Thank you so much. Next we have on the program Dr. Nandita Srivastava. She's the co-chair of the Scientific Organization Committee for this meeting, and she would just share a few words about this meeting with you all. Yeah, we can see your screen, though not yet full screen, Nandita. Yeah.
Am I audible? Hello?
Yes, you are audible, though
Okay.
we are seeing the split screen. We can see the next slide as well as the present slide. Yeah.
Oh, it's in the presentation mode. Okay. So I will go to the normal mode. Okay.
Yep, perfect.
This should be good. So, good morning, everyone. It's my pleasure to present the scientific program on behalf of SOC of the 39th Astronomical Society of India to you. Um, this is our team. We had a very active, I would call super active members of the SOC or the Scientific Organizing Committee team. And these members have helped us to plan the plenary sessions, the selection of oral and poster abstracts, and also special session. So I would like to thank each and every member of the team for being so proactive and dedicated and doing the final program in time. Now, as you all know, ASI always organizes workshops ahead of the general meeting. And normally it's a 1 day long meeting, workshop day, where we select around 4 or 5 workshops per ASI meeting. And this year has been extraordinary in terms of the number of proposals that we received for workshops. Namely, we got about 8 excellent proposals for workshops that were to be held before the main meeting. And so the SOC decided to go ahead and allot another extra day to have the workshops. And these are some of the workshops that have been concluded in the last 2 days on 18th and 19th February, ranging from the projects like what Dr. Anupama mentioned, in which the astronomical society members are engaged in. And I am told that these workshops very fruitful, which were held in the last 2 days. So the scientific sessions, about the scientific sessions, I would like to inform that we have about 21 scientific sessions, of which 3 are plenary sessions. And the scientific sessions are mainly broadly on the 5 categories that normally ASI has, like the extragalactic astronomy, sun, sun and solar system, stars, interstellar medium and galaxy, instrument and techniques, and general relativity and cosmology. The plenary sessions had star formation, transient astrophysical phenomena, and sun and the heliosphere. These are the specific sessions that we chose for having plenary sessions. And each plenary session has 3 invited talks. And I hope you will all enjoy the scientific discussion that will take place. There are thesis presentations, about 10 PhD holders that have recently submitted their thesis and would be defending their thesis. They have defended already their thesis, will be presenting their presentations on the work that they have done for their PhD. And there will be also 2 thesis award lectures ahead of each session that would be preceding the thesis presentations. There are 4 poster sessions dedicated to the poster presenters who could interact with the audience and also with the judges. And this will be in addition to the Slack channel that has been set up by the VOC. I'm not going into details of this session. I think it will already be covered by my colleague, Dr. Harvinder, who is the chair of the VOC. We have total presentations. Oral presentations are about 50%, more than 50% of the total number of papers that are being presented at the 39th ASI. And there are roughly oral sessions contain all the invited talks and the contributed talks here. We also have posters for mega projects. This is one initiative that our ASI has been taking care in the last few years. And this year, ASI has also engaged in the e-posters. So you can have a look on the mega projects posters in the poster website. Now, about the participants, there are about 606 participants to be exact who have registered for the ASI, and about 32% of them are women. We have a large number of PhD students registered for the ASI, and they form about 37% of the total registered participants. PDF are 11%. Then master's students or undergrads, they comprise of 9%. Technical staff about 4%, and people from other professions as well have registered, and they form about 4% of the total registered participants. And the faculty member are about 30%. So in fact, there is a very young population with about 70% of the total registered participants are young, which includes the young faculty who have less than 10 years of experience as a faculty. We have a very interesting talk by, it's a public lecture by Professor G. Srinivasan on stars and singularities. And this was very apt because the 2020 Nobel Prize for Physics was given to Sir Roger Penrose, Andrea Ghez, and Reinhard Genzel for their discoveries related to black holes. And it was very kind of Professor Srinivasan to have agreed to give a talk on the developments that have led to the research or the discoveries which has led to the finally to the Nobel Prize of 2020. So this talk is aimed at general audience, and it's non-technical, and it's going to be held tomorrow morning at 9:30. So I invite you to join this public lecture and also publicize to your students and colleagues and whosoever is interested to hear about black holes. This year we lost two of our stalwarts scientists and very dedicated members of the Astronomical Society of India in Professor Govind Swarup and Professor S.M. Chitre. And as you all know, Professor Govind Swarup has contributed extensively in the field of radio astronomy, and he was also the second president of the Astronomical Society of India. There is going to be a special lecture by Professor Yashwant Gupta on 22nd of February to commemorate his work and his contributions. Another lecture will be given by Professor H.M. Antia to honor the contributions of Professor S.M. Chitre, who has done outstanding work in solar physics. He was also the president of the Astronomical Society of India. So welcome to that session on 22nd February. We have, as Professor Anupama mentioned, we have a working group on gender equity under the ASI, and this group is holding a very interesting session where there will be two talks by two women scientists, Shobhana Narasimhan and Prajwal Shastri, and there will be a ASI WGG questionnaire session, which will be held on 22nd of February at 6 p.m. So you all are invited to this session. Then we have a POEC, Public Outreach and Education Committee session, which is organized on Monday, 21st February in the evening. And this year, the focus is on the education of astronomy. The theme is on hands-on experiments in UG undergraduate astronomy. And there is a very nice session with several talks by the professors who are teaching in universities and colleges to the undergraduate students about astronomy. So I would like to end this presentation on the scientific program by thanking the my team of the scientific organization and the EC, and also to special thanks to Divya Oberoi for giving helpful suggestions and very timely suggestions. We also want to thank the organizers of WGGE and POEC, and of course VOC and their team, because without them this scientific organization has no meaning. So I would like to invite you to all these sessions, participate, engage actively, and enjoy the meeting. Thank you.
Thank you so much, Professor Nandita, for a quick and yet comprehensive overview of the scientific program of this meeting. Next, I would like to invite Professor Harvinder Jassal to give us an overview from the VOC, from the Virtual Organizing Committee.
A very good morning to all. On behalf of the VOC, I really welcome you all to the first online meeting of ASI. And this is a multi-institute organization effort. We are 4 institutes who are part of the virtual organizing committee, namely ICTS Bangalore, ISER Mohali, IIT Indore, and IUCAA Pune. And this meeting is also being streamed, the plenary sessions online by Crispin. So, there are 4 EC members also, and also the SOC chairs who are part of this virtual organizing committee. So it's a very large committee. Since the geographical locations of all the organizing committee members are different, it was quite an interesting experience to put this meeting together. And I would, if there are any hitches because of this geographic separation, please bear with us, and we'll make all efforts to make sure that everything goes on smoothly. For parallel sessions, as well as for parallel sessions too, we have sent you the Zoom links for today, and we'll be sending Zoom links a day ahead of your session. And there is a Slack channel for all different sessions there, different poster sessions. For WGG session, for POEC session, there are Slack links, and people are already interacting on them. So you're welcome to interact with each other over there. And while maintaining, of course, the code of conduct. And excuse me for that. And also, please be there on this available on Slack channels when the poster session, the designated poster session is being held. So I welcome you all, and I really look forward to a very exciting meeting. Thank you.
Thank you so much, Professor Jassal. And I join her in saying that, yes, while we have put in a lot of effort and hoping in work, making sure that things will hopefully go well, we do request you to bear with any hitches when they come up and help us become better by making us aware of them and so on. So we look forward to an exciting meeting. And now we come to the award presentation part of this session, right? Where, as you know, ASI has a few awards which it awards annually or biannually. And this time, unfortunately, we will not have the ability to have people being called up on the stage and have an interaction with them. So it's going to be essentially a presentation, partly by Professor Anupama, the president of ASI, and partly by me. So our apologies for that, but there are no better options, it seems, at this point. So I invite Professor Anupama to start with the award presentation ceremony.
Harvinder, can you stop sharing this? Yeah, thank you. Okay, so welcome to this award presentation session. There are 5 awards that we are giving out in this year's session. And these are the M.K. Vainu Bappu Gold Medal. The Astronomical Society of India has instituted a fund in memory of Professor M.K. Vainu Bappu, who was also the first president of the Astronomical Society of India. And this Gold Medal Award is instituted with the objectives to promote knowledge of astronomy and astrophysics and honor the contributions made by young scientists, normally not beyond the age of 35 years, from any part of the world in the field of astronomy and astrophysics. It's my pleasure to announce that the ASI Vainu Bappu Gold Medal Award for 2020 goes to Dr. Shriharsh Tendulkar, who is just recently joined the Tata Institute of Fundamental Research and the National Center for Radio Astrophysics. I'll read out the citation for this award. The Professor M.K. Vainu Bappu Gold Medal Award of the Astronomical Society of India for the year 2020 is awarded to Dr. Sriharsh Tendulkar of the Tata Institute of Fundamental Research, Mumbai. Dr. Tendulkar began his research work as an experimental astronomer in adaptive optics instrumentation for studies on proper motion and age of magnetars, X-ray binaries, and pulsars. More recently, he has made major contributions in the emerging area of fast radio burst detection and host galaxy follow-up under the Canadian Hydrogen Intensity Mapping Experiment project. Dr. Sriharsh Tendulkar is awarded the 2020 ASI Vainu Bappu Gold Medal in recognition of his broad expertise in radio and optical astronomy, important research publications, and key contributions to the study of fast radio burst and magnetars. Congratulations, Dr. Sriharsh. We will be sending across the gold medal and the prize money to you. Congratulations. Let me move on to the next award that we are presenting. This is the ASI Laxminarayana and Nagalaxmi Modali Award. The Laxminarayana and Nagalaxmi Modali Award is instituted through a generous donation by Dr. Modali Sharma and is named after his parents. The award is given each year with the objectives to promote knowledge of astronomy and astrophysics and honor the contributions made by young Indian scientists, normally not beyond 45 years of age, engaged in the field of astronomy and astrophysics. The prize is awarded on the basis of experimental and scientific research contributions made through work done primarily in India during the 10 years preceding the year of the award. The award consists of a cash prize of 50,000 rupees and a plaque. It is my pleasure to announce that the ASI Laxminarayana and Nagalaxmi Modali Award for 2020 goes to Dr. Poonam Chandra of NCRA TIFR. Dr. Poonam Chandra's most notable work in the last 10 years is in the field of massive stars and their explosive demise as supernovae and gamma ray bursts using the Indian Giant Meter Wave Radio Telescope combined with data from other telescopes. Her group has also explored the aspects of magnetic field in massive OBA stars, which are currently 10% of the total stars known. One of the manifestations of the magnetic field is rotationally modulated gyrosynchrotron emission and a highly directional circularly polarized electron synchrotron maser emission, or the ECME. So I congratulate Dr. Poonam Chandra on this award. The next award being presented this year is the ASI Zubin Kembhavi Award. Zubin Kembhavi, 34 years of age, is the younger son of Major Rajiv and Shashmita Kembhavi. He has a brother and 3 cousins who are all at the top of their chosen professions. Zubin is probably the most gifted among the 5. But because of his extreme physical disability, he has not been able to translate his gifts to achievements. He spends his time in listening to music, in contemplation, and on occasional long drives his father and brother take him on. He has been attending a special school which he likes very much and has adapted remarkably well to online sessions made necessary by the pandemic. Ajit and Asha Kembhavi have set up the ASI Zubin Kembhavi Award as a tribute to him. The objective of the ASI Zubin Kembhavi Award is to promote observational and instrumentation work in astronomy and allied fields, to promote public outreach and education in astronomy and allied fields. The award alternates between the 2 years. The award is given annually, but alternating between these 2 areas. It also consists of a cash prize of rupees 1 lakh and a plaque. This year, the ASI Zubin Kembhavi Award is being given for public outreach and education in astronomy and allied areas. And this year's award is shared jointly by 2 awardees. The awardees are Vivek Monteiro on behalf of the Navnirmiti group. Vivek Monteiro's work includes design of low-cost and novel science and maths hands-on activities for school students, as well as taking these ideas across India to hundreds of schools. However, the main body of work that is of more relevance to the Astronomical Society of India is that Vivek Monteiro has, by himself in 1995 and subsequently through Navnirmiti, pioneered large-scale public eclipse events in India, with a special emphasis on providing cheap quality eclipse glasses, anti-superstition campaigns, and cheap non-telescopic viewing methods on a large scale. Almost all of the current activities we see in India to popularize solar eclipses among the public at large, including by the ASI POEC, were originally started by him. Congratulations to Vivek Monteiro on receiving this ASI Zubin Kembhavi Award for Outreach and Education. As I said, the award is this award is shared this year. The other recipient of the award is Samir Dhurde from IUCAA. Samir has been carrying out extensive astronomy outreach in India for 15 years now and has reached about 40 lakh people during this period. A passionate and creative science and astronomy educator, he has experience in education and public outreach at various levels in India, as well as at international levels. He is associated with the ASI POEC and the India TMT outreach activities. And most importantly, he has contributed to the improvement of the rural outreach programs in Maharashtra. Congratulations, Samir, on having received the ASI Zubin Kembhavi Award for Outreach and Education. I now request Divya to take over for the other awards.
Thank you so much, Anupama. So may I request you to stay on the slides and move them as we go forward. Okay, the next award which ASI is giving out this year is the ASI New Discovery Award. And this award is given out in order to recognize and appreciate the achievements of Indian astronomers. The society has instituted an award for the discoveries of comets, asteroids, novae, supernovae, and any other astrophysical phenomena. The prerequisite for this award is that the discovery should have been made by an Indian national in India. This award consists of a cash prize of rupees 10,000, a medal, and a citation. And this year, this award is being presented to, and if we may move to the next slide, yeah.
Yeah, 1 second.
Right. This year, this award is being presented to the team led by Dr. Kanak Saha from IUCAA. And I'll read out the citation, which is already on your screen. The ASI New Discovery Award for the year 2020 is awarded to Dr. Kanak Saha and team for detection of Lyman continuum emission from a Z equals 1.42 galaxy. This research, led by Kanak Saha, reports the detection of Lyman continuum emission from a distant galaxy using the ultraviolet imaging telescope on board the Astrosat. Published in Nature Astronomy, the reported observations probe the middle of the redshift range where no detection has been made before, making this an important discovery to bridge the gap in the Lyman continuum emission sources detected for Z less than 0.4 or for Z lying between 2.5 and 3.5. In addition, this redshift range corresponds to an important epoch near the peak of the cosmic star formation history. This landmark observation, where EUV radiation is detected for the first time from a distant galaxy, throws open a window to probe and constrain the ionization spectrum and obtain crucial insights in observational cosmology to understand the nature of sources that produce the bulk of the ionizing radiation after the cosmic dark age. Last but not the least, the results are based on the observations with India's space observatory, Astrosat. So on my own behalf and on behalf of the ASI, our hearty congratulations to Dr. Kanak Saha and the team for this ASI New Discovery Award. In addition to this, the committee made a special mention of very interesting work done by 3 students from IIT Bombay. These are Kunal Deshmukh, Harsh Kumar, and Kriti Sharma. And to tell you a little bit about what they did, Kriti Sharma, Kunal Deshmukh, and Harsh Kumar work as a team for search, confirmation, and follow-up of near-Earth objects in the Growth India project. They've set up a research collaboration with the Zwicky Transient Facility in California, and they undertake follow-up observations with the Growth India telescope and submit the results to the Minor Planet Center in less than a day after the original discovery. Their accomplishments include the near-Earth asteroid 2020 QG, which is the closest known object to have flown past the Earth without impacting it, a mere 2,950 kilometers above its surface. The previous record holder, I believe, was at around 5,600 or so kilometers. And between them, they have discovered a total of 43 asteroids in the last 1.5 years. So the ASI congratulates Kunal, Harsh, and Kriti for their achievement, and we'll be sending them a certificate and a medal. Our best regards to you both. Sorry, to all 3 of you. Next, we have the Justice Oak Best Thesis Award. The Society gives the Justice V.G. Oak Award for an outstanding PhD thesis in astronomy by an Indian student. The objective of the award is to encourage excellence amongst research students in India, and the award is given on the is Prantika Bhaumik. Prantika is being given this award for her outstanding PhD work for the development of data-constrained modeling for the origin of sun's dynamic activity and its application in the prediction of future solar cycles and global structure of the magnetic field in the solar corona. She's presently working at Durham University, England, and Prantika did her PhD under the supervision of Professor Dibyendu Nandi from SESI in IISER, Kolkata. The other joint winner of this award is Dr. Panini Singham, and he's being awarded for his outstanding PhD work for the development of hard X-ray optics based on multi-layer mirrors and using the multi-layer mirrors for the soft X-ray polarization measurements. This thesis has truly led to a comprehensive understanding of the design and fabrication of the multi-layer mirrors. He is presently working at NASA MSFC. Dr. Panini did his PhD from Indian Institute of Astrophysics in Bengaluru under the supervision of Professor P. Srikumar. our congratulations to both the award winners, and we'll be arranging for these plaques to be sent to them. And I believe that brings us to the end of this award presentation ceremony. So that we are just in time for the start of the next part of this meeting, which is basically the first of the award lectures, which is, hold on, which is to be given by Dr. Shriharsh Tendulkar, the Vainu Bappu Gold Medal awardee for the year 2020. So I invite Shriharsh to set up. Shriharsh, you should be able to unmute yourself and go ahead.
Yeah, Divya, you need to make him the
host. Yes. Yeah, he is a co-host. Yeah, he should be able to unmute and go ahead.
Thank you, Div. I can share my screen now.
Please go ahead, yeah.
Sorry about that.
Perfect.
Thank you. Thank you, Div. Thank you, Professor Anupama. It's a great pleasure to be here. So today, I'm going to talk about fast radio bursts and our work in understanding the origins of fast radio bursts. It is a great honor to receive the Vainu Bappu Award, but science is not an individual endeavor. And a lot of the credit goes to my teachers and mentors all the way from high school through graduate school and through the postdoc years, as well as my senior and junior colleagues who have worked with a lot and bounced off ideas and brainstormed, and my family who has obviously suffered a lot through an academics nomadic life, especially my wife. A lot of the work which I'm going to show today is through my collaborations with the CHIME FRB group, which includes multiple organizations, as well as the VLA Real Fast group and the European VLBI network. So a lot of the work which I'm going to be showing today is in collaboration with all of these people. So let's talk about fast radio bursts. Fast radio bursts, as the name suggests, are these very short, bright flashes of radio light that occur randomly in the sky. This animation shows the entire sky, and it's a cartoon picture of what these bursts would look like if your eyes were sensitive to radio. And they don't occur at a rate as shown in this animation, but they are quite prolific. There are about 1,000 of these bursts which occur every day in the entire sky. And some of these bursts are really bright. They can be as bright as your cell phone signal, except that they're not coming from a tower 10 kilometers away. They're coming from halfway across the universe. And that is a big mystery. So let me talk a little bit about how we know that these are coming from halfway across the universe. So when an FRB comes through a radio telescope, what you see is something like something as shown in the picture on the right. This is a dynamic spectrum of the FRB. So the color scale here is showing the intensity of radio light as a function of frequency on the vertical axis, here going from about 1200 megahertz to 1500 megahertz, and time on the horizontal axis. And you can see that the FRB arrives earlier at higher frequencies and it arrives later at lower frequencies. And this is a well understood phenomena called dispersion. So the speed of light is different at different frequencies depending on how it interacts with the cold plasma in the interstellar medium and intergalactic medium. The shape of this curve is very, very precisely known to be frequency to the -2. But the total magnitude of the offset from high frequency to low frequency is proportional to a parameter we call the dispersion measure, or DM, and that is the integral of electron density from the source to the observer. And so you're basically counting the number of electrons from the source to the observer. And this dispersion measure is not known a priori. To find an FRB, we have to search for it. So what we do is we integrate along an expected dispersion measure curve, and we create a total intensity profile. So what you see on the top is the flux. And if you hit the right DM, you'll get a sharp burst, because all the intensity at different frequencies will line up, and you search for this burst, and that is when you find an FRB. So this is computationally expensive, and which is why the first FRB was only detected about 14 years ago. The plot which I'm showing is indeed the first FRB which was detected back in 2007 by Duncan Lorimer. And because this dispersion measure is the integral of the number density, it can be a proxy for distance after we subtract the Milky Way's contribution to the dispersion measure. So the way we can do this is by integrating the electron distribution in the Milky Way itself. The plot on the left shows the electron density in the Milky Way, which has been measured by from various different parameters. And so the center of the plot is the center of the Milky Way. Our location in the Milky Way is at about 8 kiloparsecs in the y direction. So if you give me a line of sight, one can integrate this electron density and figure out what is the maximum that the Milky Way could contribute in any given direction. The plot on the right shows you exactly that sort of envelope. On the vertical axis, you are plotting the dispersion measure in log scale. And on the horizontal axis is the galactic latitude. So -90 is the galactic south pole, 0 is the galactic equator, and +90 is the galactic north pole. All the blue points are galactic pulsars. And you can see that all of them fall in a very nice galactic envelope. There are no pulsars which have significantly higher DM outside this envelope. And you can see some of the recent FRBs that have been plotted on this plot. Even at high galactic latitudes, the red points are far above what can be contributed by the Milky Way. So the rest of the contribution has to come from somewhere, and we can rule out the idea that FRB sources are surrounded by some cloud of electrons which will contribute to the DM locally. And so all this excess DM has to come from the intergalactic medium, which is incredibly tenuous. So to get the same number of electrons, the same DM contribution, you have to go really far away, up to cosmological distances. So you have to go to gigaparsec. So this was our first indication that these FRBs are extragalactic. Later, we were able to localize FRBs, very precisely pinpoint them, and identify their host galaxies. And by now we have about half a dozen or so localizations. There are a couple more in the pipeline, which I have not shown here. So the first FRB which we localized was the repeating FRB 121102, which we found was in a dwarf galaxy at a redshift of 0.2. This is a distance of about 1 gigaparsec. The others which we have found are much further away, some of them up to 3 to 5 gigaparsec away. And the nearest one which we have been able to localize is this one on the right, FRB 180916, which we localized to a galaxy which is at redshift 0.03. So 150 megaparsec, which is basically right in our backyard. And the reason I've highlighted these two FRBs, FRB 121102 and FRB 1806 in red, is because I'm going to talk about them later. They are the nearest FRBs that we have localized and we are able to study in great detail. At these distances, for FRBs to be visible to us, they have to be incredibly bright. They have to be incredibly luminous intrinsically. So this plot is showing all sorts of radio transients on two different axes. One is the luminosity versus the time scale. So you can see pulsars labeled as PSRs in this plot, rotating radio transients, RRATs, and millisecond pulsars, MSPs, at the bottom middle of the plot here. And you can see that crab giant pulses are a few orders of magnitude brighter than regular pulsars, and FRBs are many, many orders of magnitude brighter than normal pulsars. So it's about 10 to the 15 times more luminous than pulsar pulses. And we need some sort of a coherent emission mechanism that can explain this really high brightness temperature. You have extremely short time scales and extremely high energies that you need to release in those short time scales. We have no mechanism which we understand to do this. So there are a lot of different theories about what FRBs can be. You have to explain something that is 10 to the 12 times brighter than crab giant pulses themselves. And there are a lot of ways theorists have made to explain this kind of a situation. We have made a FRB theory catalog. There's a wiki. And if you don't find your favorite theory in there, please make an account and add it. There are 3 different components which you need to make an FRB or make any transient, to be honest. You need a fuel which stores the energy. You need an engine which takes the energy out of the source and makes it into a usable time scale. And then you need the transmission, which will convert that energy into electromagnetic radiation. And there are physically there are theories which mix and match these different components, which can to produce FRBs. Astrophysically, you have a lot of different possibilities. You do need a strong magnetic field because you want a coherent emission, and you need the object to be compact to explain the short time scales. But within them, there are a lot of different possibilities. One idea is that you can have a merger or coalescence of neutron stars or neutron star black hole binaries. You could have a magnetic field reconnection or a star quake kind of situation on a magnetar or a very strongly magnetized neutron star. You can have interaction of an asteroid or axion nugget with the magnetic field, which will produce electromagnetic radiation. There are some more exotic ideas about cosmic string cusps causing particle showers and then leading to electromagnetic radiation. What we want to do is try to understand whether one or many of these theories do actually work out for FRBs. As we saw before, some models are cataclysmic. So if you have a merger, you can't have a merger again. But some models perhaps would allow for FRBs to repeat. Indeed, we do see some FRBs repeat. So from the same position in the sky at almost the same dispersion measure, you can get repeated bursts. But most FRBs don't seem to repeat despite 10 to 1,000 hours of observations. And I'll talk about that a little bit more later. So are these different populations? I've shown this cartoon diagram of population as a function of quote unquote rate parameter. So you could have a distribution like orange, where you have one population of repeaters and there's another population of some cataclysmic event which never repeats. Or you could have two different ends of the same population, which is shown in green. So you have rare repeaters on the left, which repeat say once in a century, and we see only one burst out of them in our lifetime. And on the right-hand side, you would have the more prolific repeaters, which repeat quite often, and hence we see them as repeaters. So we don't know whether these two populations are actually separate astrophysical channels. Separately, apart from trying to understand what FRBs themselves are, there is a huge interest in using FRBs as cosmological probes. FRBs are prolific and they are coming to us from halfway across the universe, and they're these polarized radio waves which interact with every electron and every magnetic field that they pass through. So using scintillation and scattering and DM distributions, you can try to understand the turbulence, baryon distributions in the universe. You could try to probe helium-2 reionizations at redshift 3. You could also use Faraday rotation and Faraday conversion to try to understand magnetic fields in the intergalactic medium, in galaxy halos, or even the local environments around FRBs. Another very nice idea, which would be fantastic for cosmology, would be to detect an FRB that is gravitationally lensed, especially a repeating FRB that is gravitationally lensed, which would allow us almost real-time measurements of the universe expanding. To do all of this, you really need a large sample of FRBs, and that has been our effort for the past 4 years almost. So I'm going to talk about the Canadian Hydrogen Intensity Mapping Experiment, or CHIME FRB, which we have been building and constructing over the past 4 years. So the results which I'm going to talk about, of course, are necessarily biased because I'm short of time. but I should note that there are also other efforts which are being done across the world and in India. So CHIME is a transit telescope which was built primarily for doing baryon acoustic oscillation mapping. So it consists of these 4 cylinders which are stationary. Each of them is 20 meters wide and 100 meters long. So it's a bit like the UT radio telescope, except that it's flat and it's stationary. And each of these 4 telescopes has 256 dual polarization feeds which operate from 400 to 800 megahertz underneath them. And between these 4 telescopes, it covers a field of view of about 250 square degrees, which is a key driver for detecting FRBs. You are covering huge swaths of the sky simultaneously. And all of the processing of the data which comes through this, it's about 130 gigabits per second, happens in these white shipping containers you can see to the right-hand side of the telescope. And I should note that this telescope has been built primarily by astronomers, so undergraduates, graduate students, postdocs, and all the way up to emeritus professors have worked hands-on on the metal to build this telescope and make it work. Just to give you an idea of how CHIME sees the sky, this is the animation of the sky, the radio sky, rotating above the CHIME location. So the inner circle is the horizon of CHIME, and you can see a very narrow field of view of CHIME, which it goes from the northern horizon to the southern horizon, and it is divided into 1024 stationary beams in a configuration which is 4 beams wide and 256 beams from north to south. And this basically gives us a search capability equivalent to 1024 green bank telescopes. It's a collecting area of about 100 meters by 80 meters, and we are searching 1024 beams simultaneously for FRBs. So let me talk about CHIME FRB results now. We have had a lot of success in working on FRBs, and there have been a lot of papers which have come out. I won't be able to talk about all of them, but just to briefly mention, we had the first detections of FRBs at 400 megahertz. When we built the telescope, we didn't even know whether there were any FRBs at these low frequencies. Since then, we have detected 17 new repeating FRBs. One of them had a 16.5-day periodic activity window in FRB 180916, and I'll talk about a little bit more about that soon. Last year, we also had a galactic FRB from a magnetar SGR 1935 plus 2154, which was basically the brightest radio transient which has been detected on Earth. I'm pretty sure I can honestly say that. We have also had detections of 7 new galactic rotating radio transients, RRATs, and a new pulsar with a massive binary companion. There have been many more offshoot papers, but the thing I'm going to talk about a lot today is the first catalog paper, which we have just submitted, and the related papers on FRB populations, which are either submitted or are in preparation. There are 3 main ways of studying FRBs. One is to study the populations themselves to understand the volumetric rates, distributions, energy distributions. You can do cross correlations with galaxies. You can study properties of individual bursts. You can do burst morphology, polarization, scattering, distributions, or you can do deep individual studies of specific FRBs that are nearby, and you can study them very well. So I'm not going to talk about each of these, but I would highlight some of the papers which our students are writing, and I hope that you will keep an eye out for them because they are really fantastic papers. So let me talk about the FRB catalog. This is submitted right now and hopefully should be out for public very soon. The first CHIME FRB catalog has about 535 FRBs that have been characterized for the first year of CHIME's operation from July 2018 to July 2019, and we are still playing catch up with the rest of them. This plot shows the detections of these FRBs. The blue ones are as yet non-repeating FRBs, and the orange triangles are the 17 repeating FRBs, which I mentioned before. And you can see that they're fairly uniformly distributed across the sky without any significant lack of FRBs along the galactic plane. So the CHIME, because of the way CHIME operates in the transit telescope sense, different parts of the sky spend different amounts of time going through the chime beam. So towards the southern horizon, the sky moves fairly quickly, so we have less exposure. Towards the North Pole, we have much higher exposure. So the range of exposures is really wide, from about 10 hours in the southern sky, 10 hours over the entire year, to about 2000 hours over the entire year. So one might ask, do we see more repeaters with more exposure? So if all FRBs were repeaters at different rates, you might expect that the ratio of repeaters to non-repeaters might increase as you go to higher and higher exposures. So we could try to figure out from the deck distribution whether repeaters and non-repeaters have the same kind of distribution. And it turns out that from our observations, they are consistent till now. So there is no significant difference between the distribution of repeaters and non-repeaters in different exposure times. The plots which are shown here are just basically showing you a color scale of the exposure from the southern horizon to the pole, and the polar regions are highlighted separately. We can also use injections to characterize the sensitivity or the detection probability of chime for an FRB of a given parameter. So FRB with a given DM, given width, given scattering, fluence, and sky position, and we can create observationally corrected distributions. So what I'm showing here is a plot of the observationally corrected DM distribution. You can read further details in our paper. And what we see is that the observed distribution by chime peaks at about about 700 DM units, and above a DM of about 2000, we detect very few FRBs. And this is probably because we are reaching the end of the luminosity function as seen by chime. We need more sensitive telescopes if we want to go further. And with this, we can also do a beam corrected measurement of the rate and power law index. So here we are characterizing the rate in the sky above a fluence F as F to the alpha, where alpha is the power law index. And we measure a rate of about 820 FRBs every day in the entire sky above a fluence of 5 Jansky milliseconds at 600 megahertz. And the power law index that we measure is consistent with the Euclidean value minus 1.5, which we expect from a flat universe in the local neighborhood, except that it does change slightly with DM. So at high DM, if you take only the high DM FRBs, you get a steeper alpha, which is what you expect if you are reaching the end of the FRB luminosity distribution. Now, if you have a lot of FRBs, you can also try to study their morphology. And so what we have seen is that some FRBs are broadband and single component. So here I'm showing you waterfall plots, the dynamic spectra of these FRBs with the dispersion removed. And it goes from 400 megahertz to 800 megahertz on the vertical axis and about 10 to 50 milliseconds wide on the horizontal axis. You can see some of them cover the entire frequency band from 400 to 800 megahertz. Some of them are fairly narrow band. They're very splotchy. They're narrow band and they have multiple components. So one of our students, now postdoc Ziggy Plunis, has separated these into 4 different archetypes of FRB. So you have these single component broadband FRBs, you have single component narrowband FRBs, you have multiple components with similar spectra, or you can have multiple components with this downward drifting structure, which is now called the sad trombone effect, because it sounds like the notes of a sad trombone going pa, pa, pa in lower frequencies. So what we have seen is that these single broadband components are often seen from non-repeaters, and the others, the narrowband components, are often seen from repeaters. Now, this is a very generic statement, but I will quantify that later. And you should be aware that there are beam effects which can change a single broadband component into a single component narrowband kind of structure. But despite that, there are significant differences in FRBs from repeaters and non-repeaters. So here you can see a characterization of FRB spectra on the vertical axis. There is a parameter called spectral running. We don't need to know what exactly it is, but towards the top, you have a more power law-like spectrum, so more broadband. Towards the bottom, you have a Gaussian-like spectrum, so it's more narrow band. On the horizontal axis is the intrinsic width. So narrow pulse on the left, broad pulse on the right. And this is after removing scattering. So any interstellar scattering has been removed. The green pulses are the one-off events from FRBs, where we have not seen repetitions yet. The orange pulses are bursts from repeaters. And just to be clear about possible selection effects in detecting repeaters, we have also plotted the first bursts which we have detected from the repeaters, all 18 of them in purple. And what you can see is that the histograms, the probability histograms on the top and the left, on the right, are significantly different. If you do a KS test, they are absolutely different. So we can say that repeater bursts are temporally wider and spectrally narrowband. There is another way of showing the same, characterizing the same thing. You can measure the bandwidth over which it is detectable and the duration. And you can see that the one-off events shown in green and the repeater bursts shown in orange are significantly different. So there are some differences between the bursts from repeaters and the bursts from as yet non-repeaters. But does that mean that there are two different populations? Well, that is not necessarily true. Just to play a devil's advocate, you can point out that burst properties could change with the repetition rate. So you could have rapid repeaters which have complex bursts, and perhaps the rare repeaters which maybe are older population or have a magnetic field which has decayed, have simple bursts. That's a possibility. This could be some sort of a propagation or beaming effect. So if you had narrower beaming, you would have rarer repetition, and you would have more these could correspond to simple bursts, or perhaps conversely, a wider, more complex beam could provide a more prolific repetition and more complex bursts. So there are ongoing studies with trying to understand polarization differences, rates, and everything. So we would have more information about these. This can also help guide repeater follow-up. If you detect something with a complex burst, that might be more likely to be a repeater, and hence you would want to follow up, but you should avoid biasing catalogs. So let me now talk about a few of the individual FRBs which we are really excited about. So there was this galactic FRB last year where we detected a really bright radio burst from SGR 1935 plus 2154, which is a magnetar which had been active in X-ray bursts. Now, this was not as bright as most FRBs. It was at the lower end of the energetics, but still, it is really important because this is the first FRB from a canonical magnetar after a lot of speculation. And this was also the first FRB where we were able to detect a multi-wavelength component. So this is beautiful. This is a beautiful plot from the integral team where they show that the X-ray burst has multiple peaks which line up very well with the two radio peaks which were detected by CHIME, which is the orange curve here. And there is an offset. So the radio comes first, just 6 milliseconds before the X-ray peaks. And the interpretation of this is that we actually think that the magnetic reconnection model works a lot better than the synchrotron emission model in this case. But we still don't understand why this burst was the one which had a radio counterpart. There are many other X-ray bursts without radio counterparts, and there are other radio bursts without X-ray counterparts. And we really don't know what sort of funny situation is happening over there. So magnetars can create FRBs, but not in all bursts. And the rate of these bursts is enough to explain FRBs in general, but you cannot explain the prolifically repeating FRBs, especially the periodic ones, which I'm going to talk about next. So two of the FRBs which I mentioned earlier, the repeating FRBs, FRB 121102 and FRB 180916, have been shown to have periodic activity windows. So they are not periodic like pulsars that their pulses come at exactly the right time, but their activity windows are periodic. So there'll be an activity window which will open up, and for a couple of days it will burst sporadically, and then it will shut down again for a while. For FRB 180916, on the bottom here, the period is 16.35 days. And for FRB 121102, the period is 160 days. Now, then you would ask, what is this period? Is it an orbital period of a binary? Is it the rotation period of a really slowly rotating magnetar, or some sort of a precessing isolated magnetar? And we have been able to do extremely deep VLBI plus HST enabled studies, because we know the position very well to less than 5 milliarc seconds. And with HST and Gaia, we have been able to astrometrically correct the optical images. What we see is that both of these FRBs have about 250 parsec offset from the star forming regions. Now, the magnetar scale height in our galaxy is about 20 to 30 parsec. And magnetars are very young. They stop their activity within 10,000 years of the supernova. So they can't really travel 250 parsec away from where they are born while still being active. And so the only thing we can think of, which is likely, is that these FRBs are coming from high mass X-ray binary kind of systems, which do have 400 parsec offsets from their local star forming regions. So we think that we are now trying to understand individual FRBs and trying to figure out what their emission mechanisms are. So I would like to highlight that detecting FRBs is not enough. Precise localization is crucial for understanding what these FRBs are and what we can use them for. Now, of course, most interferometric telescopes are built for small fields of view, so they cannot efficiently find FRBs. So what we are now doing with CHIME FRB is to build outrigger telescopes. So CHIME is on the west coast of Canada, and we are building outrigger telescopes in Algonquin and possibly in Green Bank in the US, which are about 3,000 kilometers away, which will localize about 1,000 FRBs every year in 2 years. But most of these FRBs will be far away at redshifts of 0.5 to 0.7. And those are really hard to study. So we need a separate focus on bright nearby FRBs, which are rare. So we need a large field of view. So we need to cover almost the entire hemisphere. So from the Indian perspective, UGMRT is excellent at localizing, repeating and faint FRBs. So we can study polarization properties, we can localize them, we can try to understand these FRBs in great detail. And with the UT radio telescope upgrade, the UT wide field array, we can study FRB repetitions, periodicity searches. We can do a lot of scattering and scintillation studies. And with SWAN, the effort at RRI and across India, and Gauri Bidanur, like broad arrays perhaps at higher frequencies, these we would be able to detect and localize nearby bright bursts. So to conclude, we have been trying to probe FRBs in many different ways. The population studies are beginning to tell us about burst energetics and rates. There are significant differences between bursts from repeaters and as yet non-repeaters, but we can't yet conclude that they are different astrophysical channels. And what we need to figure out their astrophysical channels is actually precise localization of these nearby FRBs and try to understand their local environments and what sort of astrophysical objects are giving rise to these FRBs. With that, I will stop.
Thank you so much, Shriharsh. Yeah, thanks a lot for an excellent overview of the field of FRBs and the exciting world of CHIME FRBs. And from having just a handful to going to 535 FRBs in a year's worth of data is really exciting. And also, thanks for giving us a sense for where the field is headed and what do we need to do to extract the most science out of these. Now, I realized that there was something I should have said earlier, which is about questions. Yeah. So if you have any questions, we have time for just a couple. Please raise your hand on Zoom and one of us will unmute you and then you can go ahead. So I saw the first hand by Prajwal and I'm going to yeah, Prajwal, you can please unmute and go.
Yeah, so one question was that in the atlas of profiles that you showed, some have very asymmetric profile in the time domain, as in there's a very sharp rise and then a less sharp fall. So is that real, as in explaining that as an artifact of the measurement process can be definitely ruled out? And my second minor question was, there was a catalog called FRB Cat, which I understand will not be actively updated. So is there an alternative now which will be comprehensive, including the CHIME discoveries and others as well? Thanks.
Thank you, Prajwal. Yes, so to answer your first question, the sharp rise and exponential decay which you see is not an instrumental artifact. It is because of scattering, multipath scattering in the interstellar medium, and it affects lower frequencies more than higher frequencies. So you can see in this plot, in the first plot here, that the scattering tail becomes bigger and bigger at lower frequencies, and that is a very characteristic thing which we can use to measure interstellar. So that is definitely a measurement of ISM turbulence. The other, to answer your other question, the FRB CAT has been active, but it might not be updated completely. The alternative, the new alternative that the FRB community has agreed upon is that the transient name server, which is hosted by the Weizmann Institute, will host all the FRB catalog, and all these FRBs from Chime will be are already posted there, and they will become public very soon.
Okay, thank you.
Thanks. The next hand I saw raised was by Varun. Varun, you should be able to unmute and go.
Thanks. So Shriharsh, in one of your early slides, slide 6, I think, where you showed an example of a FRB, the post-FRB radio level actually was below the pre-FRB level.
Yeah, so this is an instrumental artifact.
The slide before after this
was this the slide? I think this was the slide, right? Yeah, so this is an artifact of the 1-bit digitizer. This FRB was really bright, and this data was taken with Parkes a long time ago in 2001, when digitization was done with a 1-bit signal, and you have a 1 second average running average. And so this, because this FRB was so bright, it changed the running average, and so the post FRB baseline had changed significantly.
Thanks. Indulekha, you could please go next.
Yeah, regarding the distance from the nearest star-forming region, there are runaway O stars. So if you combine the speeds of runaway O stars which are kicked out from the clusters, along with, let us say, a kick during the formation of the compact object, would that kind of speeds account for the distance between the FRB and the nearest star-forming region?
Yeah, that is an excellent question, Indulekha. So we did consider that, and that can explain the separation. So there are runaway OB stars which typically are a few % of the entire population. So the only challenge there is explaining why the other OB stars don't form, the other 90 to 95% of the OB stars don't form FRB-like magnetars. So it is a formation channel which is possible, but it seems to be less likely than the others.
Thank you.
Shantanu, you could go next. Please unmute yourself.
Yes, sorry, I had a problem unmuting. So have there been searches for counterparts at high energies, X-rays and gamma rays? And also, I mean, just to quick, have people looked at these all-sky surveys for, I guess, serendipitous optical counterparts?
Yeah, so that's a great question, Shantanu. So we have looked for X-ray counterparts to these bursts, and we have not found any yet, except for the one which I showed with SGR 1935. The problem is these objects are too far away for X-ray telescopes to detect any significant number of photons, and we really need nearby FRBs. One of the things which I didn't mention right now is that we have detected a FRB in M81, which is at just 4 megaparsec, which is a significant improvement over the past record holder, which is 150 megaparsec. And so we should be able to train X-ray telescopes in that location and hope for a radio and X-ray burst at the same time. So, and we have searched for serendipitous X-ray and radio counterparts as well. With optical, we have done a little bit of work. We have trained the Gemini telescope at this FRB 180916 and tried to look for bursts. And there is a paper which we are putting out right now where we had a radio burst but no counterpart in the optical. The challenge is that at high energies, you need a lot more energy. In radio, it is fairly cheap in terms of energetics to produce something that is detectable.
Thanks. I'm going to take the last question from Amrish. Amrish, you should be able to unmute.
Yes, am I audible?
Yeah.
Hi Shriharsh, my question is about your slide 6, where you essentially show the number density contribution in the DM from the galaxy. So I was wondering, if you remove the contribution due to our galaxy, you would essentially expect a uniform distribution of red points in this figure, right? Red circles.
Right.
So when you add the contribution due to our galaxy, do you expect the same shape as the envelope of our galaxy in the red points as well?
Yes, you're right that we should be able to see, you know, the distribution of DMs outside the galaxy should be uniform. That is true. But right now we are not doing this exercise. So because our till when this figure was produced, the chime was not completely operational. So you see a very weird distribution of points from specific telescopes. But now we should be able to do that.
Okay.
And so we can show, there's a paper coming out by Alex Josephi, which will show that we can, across galactic latitudes, you can still see the same distribution of FRBs.
So, but by removing the contribution due to our galaxy or after adding it?
After removing.
Yes, okay.
Yeah.
Great, yeah, thanks. I'll just remind the participants that we also have a Slack channel where we have made actually a thread for every talk, which is being given in every session. So please, if you have any questions, please feel free to go and post them to those particular threads in those channels. Let's all thank Shriharsh once again for an excellent talk. And I now request Professor Poonam Chandra, who's also our awardee for the ASI Laxminarayana and Nagalaxmi Modali Award, to please set up and start her presentation.
Thank you, Dev, and good morning, everyone. I'm really thrilled to get this award. Let me start with that. And I would like to thank a lot of people because of which I could get this award, starting from people who have...
You're not sharing your slides yet, Poonam.
Oh yeah, I have to share. Right, sorry. I am so sorry. Can you see the...
Yeah, we can see it. It's not yet full screen. Yeah.
Right. Slideshow. Is it good now?
Perfect.
All right. Yeah. So I would like to thank a lot of people who have nominated me, people in the committee who decided to give me this award, a set of amazing students, because of otherwise whose amazing work is the reason that I got this award, collaborators for scientific discussions, and team GMRT for generously giving me time, and the operators at the GMRT who are working very hard to make these observations happen in best possible way. So thank you everyone, and I'm really happy. So I will start with saying that stellar evolution affects in our galaxy, in our universe, in more ways than we can envisage. The stars, whether they are low mass stars, intermediate mass stars, or high mass stars, they have a different evolutionary path. Each star has a very exciting evolutionary path, but it is the massive stars which have very exotic and fast forwarded evolutionary path, and they end their lives with a bang, like literally with a bang. So what we have been doing in past few years is that we are trying to understand the stellar evolution and end products of hot massive stars, because they are really one of the most exciting objects in stellar evolution. And we have a two-way approach. One is that we are trying to understand the stellar evolution of hot stars, because one needs to get into the nitty-gritty details of main sequence stage, because it offers the best opportunity to gauge the relevance of various possible evolutionary scenarios. We are also studying the exotic deaths of massive stars as supernovae, be it thermonuclear core collapse or gamma ray bursts, and trying to map the various explosive ends to their progenitors, because they have very important implications in supernovae, gamma ray bursts, their gravitational waves coming from the mergers of these their compact remnants, and in some cases fast radio bursts. So the second part I'm not going to talk about today, since I have another talk tomorrow in the morning plenary session. I will be talking about the second part tomorrow, and I'm going to focus on the first part. Massive stars are literally the chemical engines of our galaxy, which enhance the chemical metallicity of the galaxies. They trigger star formation with their ends as supernovae, gamma ray bursts, or the second deaths as neutron star mergers, giving rise to gamma ray bursts, or in some cases possibly fast radio bursts. They do have a lot to contribute, and to understand these stars, one need to get inputs from observations as well as theory. And there are some aspects which one can intuitively think will contribute when you have to understand the evolution of these stars. These are mass loss rate from these stars, since they are very close to their radiative diffusion upper limit in terms of luminosities. The mass loss rates are quite important. The rotation, metallicity, binarity, since it turns out that most of the massive stars will be in binary system, and last but not the least, magnetic field. Now, magnetic field is a very important ingredient because it has been shown in systematic surveys, spectropolarimetry surveys, that approximately 10% of massive stars they host magnetic field. These are very strong kilogauss kind of magnetic fields, but they are very simple in nature. They are dipolar magnetic field, and that poses a problem. The problem it poses is that while it is easier to generate magnetic field in sun-like stars because they have outer conductive layer, the massive stars have outermost radiative layer, and it's not. Then one doesn't know how to generate magnetic field in these stars. So that kind of goes counterintuitive in that sense. But it is important to understand these stars with magnetic fields because they can explain some of the very exotic like objects in our universe, which are like magnetic white dwarfs, magnetas. The way magnetic fields in the stars will affect the stellar evolution will certainly change the nature of their end products. And some of the ways they can affect is, for example, magnetic braking. They can slow down the rotation of the magnetic stars, and in general magnetic stars are slower rotators than their non-magnetic counterparts. Of course, there are some exceptions which one needs to understand. Then also the thing is, these magnetic stars is a very nice way to stop or quench the mass loss rate of massive stars by forcing these plasma to follow this magnetic field of lines. And this reduced mass loss rate, one, it will affect the stellar evolution, but second, it also has the potential to solve one of the mysteries. For example, one of the mysteries mysteries right now is the LIGO heavy black holes, and it is difficult to understand this. But if the stars are to start with magnetic, then the mass loss rate will be much reduced, and they can explain some of these big black holes formation. And Veronique Petit et al. Has run some simulations, and they have shown that in a 80 solar mass stars in a solar metallicity environment, the mass loss rate can be quenched up to 20 solar masses. So this is a huge gain. So hence these magnetic fields are quite important to understand. The problem, as I said just now, is to understand the origin of these magnetic fields. There are few ideas, but the two most important thought process where people are tilting towards is fossil field, where the ISM magnetic field can give rise to or contribute. It will, by a magnetic field flux conservation, can give rise to these simple kilogauss field. The second is the stellar mergers, where the differential rotation between the two stars can also give rise to the field, the magnetic field in massive stars. Both have their plus points and negative points. The problem with the fossil field hypothesis is that the star which is formed from this ISM it has to undergo this convective, fully convective pre-main sequence protostar evolution, and in that time, these seed magnetic fields have to, sustain and stay, and eventually become the stable magnetic field. Even though it's not a hopeless situation, some of the numerical and semi-analytical calculations have shown that the magnetic fields are able to relax and create a dipolar magnetic field. Another big challenge is that out of around 50 known magnetic stars, massive stars, around 12, a dozen are magnetic binaries. But in those, most of the time, only one of the star is magnetic and other is not. If they were formed from the same ISM, how is it possible that one star has become magnetic and other has not? And it is a mystery to understand. So it is a challenge, but we do know that certainly some stars must be coming from the fossil field, because this star which I am saying, ALS 9522, it is a pre-main sequence star. It hosts a 4 kilogauss dipolar magnetic field, and it is in an evolutionary path to become a main sequence B star. It means, it is the most likely explanation is a fossil field. In mergers also, this is the second exception. The problem is that it's difficult to act the merger act in action. But the thing is, recently there was a Nature paper where this team Schneider et al. Their team has taken two stars, 9 and 7 solar masses, and they merged together, and they showed on the type plot that a kilogauss kind of magnetic field can be generated, and which will remain stable for a long time to come. So this is possible. It is extremely difficult to understand these implications of magnetic field generation, because they will have very important implications in the stellar evolution model. So that is what the motivation is, to study the magnetic field in massive stars. A lot of theoretical work has gone into understanding these stars, and from the interaction of this magnetic field with the wind, it has been suggested that it will create the wind interaction with the magnetic field is going to create a magnetosphere, and the magnetosphere will have certain properties. For example, closer to the star where magnetic field will dominate, the field lines will follow, the plasma will follow the magnetic field lines, and this is called the inner magnetosphere. But since magnetic field decays faster than the wind density, beyond certain point, the wind will dominate and magnetic field will kind of open up, and this is an outer magnetic uh, magnetosphere, and there will be a boundary which is called Alfvén radius, where the two will be equal, and this is probably the last line of closed magnetosphere, if you want to take it that way. So this is, in fact, this is a much two-dimensional picture, makes it a much better. This is the last closed inner magnetosphere. This is the Alfvén radius, and this is the outermost. Now the thing is, manifestation of magnetic field in massive stars. In the massive stars, these, from the pole, these magnetic field lines are coming. They are hitting in the equator, and because of this hitting, the temperature is increasing. They go to, high temperatures, million Kelvin temperatures, and they give rise to the X-ray from the inner magnetosphere. The electrons in the presence of magnetic field will get accelerated, and when they travel back, these electrons in the presence of magnetic field will give rise to gyrosynchrotron radio emission. So the X-ray is coming from the inner magnetosphere, the radio is coming from the middle magnetosphere. The both wavelengths probe different regions of the magnetosphere. There's one very important implication of magnetic field, since it is a dipolar magnetic field, and the chances that the rotation axis is aligned to the magnetic axis are very, very limited. So because of the misalignment, one will see a modulated emission. And this modulated emission has been seen in radio on the top and X-ray at the bottom in several magnetic stars. So this is the background, but I am going to focus on the radio studies of these stars because the most important reason is that radio is the best proxy to understand magnetism in massive stars. Magnetic field manifests in the best possible way in the radio bands. Of course, one expects X-ray, one expects H-alpha from recombination, but there are many magnetic stars when X-ray and H-alpha have not been seen and radio emission has been seen from these stars. Radio emission, it is difficult to disentangle the radio emission in these stars. For example, you will have the thermal emission because of the plasma, gyrosynchrotron emission, the emission due to if they are in the binary system, and then there is an exotic emission, which is a coherent emission, which is called electron cyclotron maser emission. And to understand all of these emission has its own virtue. But unfortunately, very few radio studies have been done in the past and no low frequency surveys have been done. So to homogenize the study of these magnetic stars, we have decided to do a detailed studies, and we have decided to probe the wavelength of 0.5 or actually now I would say 0.3 to 40 gigahertz. We started with a pilot survey with GMRT, then we carried out a much longer survey with the JVLA from all the way from 2 gigahertz to 40 gigahertz. And then we have also carried out a survey of many magnetic stars with the GMRT. This is the lowest study, and it provides us best opportunity to understand the outer stellar corona. So these are some of the results I'll be talking about. So with GMRT, we have detected many of the B stars, but we have not detected O stars. But if you imagine that GMRT works at low frequencies where absorption is more dominant, it is probably not a surprise. With VLA, we have detected a couple of O stars, a few B stars, and we have also tried to compare the different properties of these stars in terms of luminosity, in terms of the location of the Alphen radius, location of the Kepler's co-rotation radius, and so far. And we have also estimated the mass loss rates of the detected stars. We have compared with them with the empirical mass loss rate to understand whether the possible emission is thermal or non-thermal. Because if it is thermal, then the mass loss rates, theoretical mass loss rate should match the one which we have detected, for example, in this case, HD 37742. But in other cases, you can see that mass loss rate observed by measured by us are much larger, orders of magnitude larger than their thermal counterparts. So that shows that magnetism is manifesting themselves in non-thermal radio emission. We have also seen the rotational modulation at low frequencies in some of the stars. And while doing this study, the biggest surprise came in the form of HD 133880. Here, if you see along the longitudinal magnetic null, we saw order of magnitude enhancement of the radio flux. And this cannot be gyrosynchrotron because gyrosynchrotron should be maximum where the magnetic field maximalizes, which is around here. So this was something different. The only explanation possible was that is it possible that it is coming from electron cyclotron maser emission, and which we actually initially thought very unlikely because before this star there was only one star, a hot star which had shown electron cyclotron maser emission, and that was CU version, and that was reported in the year 2000, and for 15 years there was not a second detection. So this seemed very unlikely, but if it is electron cyclotron maser emission, then this is an extremely important discovery, and it opens up a new phase space for us to understand this field, because the thing is electron cyclotron maser emission can be generated in these magnetic stars by the following method. The electrons which are responsible for the radio emission, some of these electrons, these electrons, since they will go to the magnetic mirroring, some of these electrons will be lost and they will create a loss cone anisotropy, and they will create the electron cyclotron major emission, and the frequency of emission is going to be proportional to the magnetic field, which means you can imagine that the lower frequency will arise farther from the star because the magnetic field is lower than the higher frequency. And this is very exciting because now it gives us a way to probe the magnetosphere at different heights. And if we can figure out that which magneto-ionic mode is getting excited in this ECME, that can give us the constraints on the plasma emission. And the way electron cyclotron major emission is generated, it's highly directive, nearly 100% circularly polarized. And because of the way our line of sight and that the star is located, we are only going to see the directional emission either at the top if the X mode is excited, that is, extraordinary mode, or the ordinary mode. Of course, let me just tell you that extraordinary mode will be excited at frequencies which are much higher than plasma frequencies. But whereas if the frequency is closer to or smaller than the 1/3 of the plasma frequency, then ordinary mode is expected to be excited. So with this background, we decided to do the detailed study, and Bernali carried out this detailed study of this star, where we carried it the observation for a full rotational phase, and we confirmed that we are seeing the electron cyclotron major emission. And after 15 years, we had actually basically detected the second magnetic star with electron cyclotron major emission. And this was a very interesting study, because then we decided that what are the similarities between the two stars known, and what is that one or two or few physical properties which can give rise to electron cyclotron major emission. Since we did not know that, we carried out a systematic study of some stars. I think we have observed almost a dozen or little more stars. This formed Bernali's PhD thesis, and our plan was to search for the ECME. Now, 15 years down the line after CU version, in past couple of years, 6 more stars with ECME has been seen, confirmed star, out of which 3 have been detected by us with the UGMRT. We also have 2 more new candidates, and we are carrying out more observations and analysis to confirm ECME from them. And since we have detected most of them, we get to name them. So we have named these main sequence radio pulse emitters, MRPs. And this term we had to coin last week itself, because our article was is coming up in SK Contact magazine, and that time we needed to think of a nice term. So this is what we came up with. So we have carried out detailed. Our aim was to search for the ECME. With whatever star we discover ECME, carry out a detailed study, and we find out that the range in which ECME works, and if we can find out the magneto-ionic mode of emission, constrain the plasma density, and if we do not see the ECME as expected, what are the physics reasons which is causing us the deviation from this ideal ECME. So this was the goal. And these are some of the stars which we have detected. The top left is HD 142990, which is the most massive stars known to have ECME. Its mass is around 6 solar masses. This is 35298. These 2 are the tentative discoveries, and which we are going to be publishing very, very soon. So in addition to 133880, these are the 4, 2 confirmed and 2 nearly confirmed we have with ECME. For HD 1330 and CU version, we have carried out wide band studies all the way from 300 to 4000 megahertz using UGMRT and VLA. If you were attending the SK session, Bernali gave an excellent talk on CU version system, and she will be publishing that very, very soon. So I'm not going to get into that, and I'll be talking about HD 133880, the second ever star to show ECME. One thing is that, we broke the jinx of having only one circular polarization to be seen in ECME. We saw both left circular and right circular polarization. We also saw that at low frequency, left circular polarization dominate, and at high frequency, right circular start to dominate. For example, if you see this second magnetic null, the blue is left circular polarization, and as you go higher and higher in frequencies, eventually the left goes slower and the right circular polarization starts to dominate. And one needs to understand this, and I'll get back to it in a minute. Also another interesting thing is, since ECM is so directional, that it can be used to see the evolution in stars rotation period. And within our 3 years of data, we saw that the ECME enhancements are shifted by a phase of around 0.02, and it indicated the changes in rotation period. And we are investigating this aspect of this particular star. We saw the X mode of ECME, and we constrained the plasma density to be around 10 to the power 8 per centimeter cube. For the first time ever, we saw an upper cutoff of the ECME. Here you can see the cut. This is the background. And you can see we saw the upper cutoff of the star ECME, which is lying between 3 and 4 megahertz. In this particular case, it is probably beyond 4 gigahertz. And this upper cutoff tells us that this is the highest frequency where electrons can be in this resonating condition to be able to give the ECME. So this was the first upper cutoff seen in any star with ECME. We have not yet seen the lower cutoff, but hopefully we will see in some of these stars. Now the thing is that we did not see the ideal behavior which one is expected to see in ECME, and so far in the past this has been explained as some deviations in the perfect dipolar magnetic field. We wanted to explore, and this heavy lifting in this work has been done by Bernali and another student from NCRS, Surajit Mandal. So I should really give credit to them for this work. So in this case, what has been done is that we saw that pulses at different frequencies arrive at slightly different rotational phase, and this has been seen earlier in CU version and has been talked about, and has been said that it is because when this ECM is generated, it is coming via the inner magnetosphere, and since different frequencies undergo different refraction, that's why one is seeing at slightly offset phases. But so far the work which was done, it assumed a constant density, a single refraction at the boundary when it is entering to the inner magnetosphere. It did not consider any complicated model which is more likely at play. So what we did this work, we basically first time we proposed and we gave the community a 3D propagation model where we took into account of continuous refraction. We also proposed the case for axisymmetric magnetosphere as well as asymmetric magnetosphere, because this is the kind of density profile at different magnetic azimuth angles, and you can see a very different asymmetric profile. This is the density profile, and we tried to put the ideally generated ECME through this code with asymmetric and axisymmetric magnetosphere, and we were in for a surprise. A single refraction propagation model is as expected as in the left curve, and which is what is a very simple model. But if you have a asymmetric density distribution, you can see for example at lower frequencies, one of the polarization is gone. It is not detected here. Here you can see only the RCP. It is not coming at the nulls. It is coming at different positions. It is because some of these ECME, for example, in this case, left circular, is probably having a much more dense magnetosphere or inner magnetosphere, and getting absorbed, and one is not seeing that. We also saw some secondary pulses. We didn't see this ideal kind of cases, and so we are seeing the opposite sequence. And all of these are manifestations, different manifestations of the asymmetric density distribution. So far, every ECME which has been talked about, a non-ideal condition has been talked about or attributed to the non-dipolar magnetic field kind of structure. We showed that even if we ran our code for a perfectly dipolar magnetic field, but just by the density distribution, taking a more realistic density distribution, because electrons are coming here and then it's likely to have more highly asymmetric density distribution in this way, we were able to recreate some of the features of observed ECMA. And this is an extremely important work. This is still in the, I would say infancy, and we need to work more on it. But it is a very important tool to the community, where it can help us in understanding the ECME. So I would like to summarize this work in the following way, that we have carried out a systematic radio emission studies of magnetic hot stars for the first time, exploring their sub-gigahertz to gigahertz band properties using VLA and GMRT. We have, in terms of gyrosynchrotron, we did detect radio emission from 9 stars. And in terms of ECME, we had 3 confirmed ECME, 2 ECME candidates. And for the first time after, so many years, decade, a statistically significant sample of these MRPs exists, that one can think of carrying out much more detailed study and try to probe the physics of these objects. From the right circular, left circular ECME, we have been able to understand the density constraints of the plasma surrounding these stars. We have seen the possible rotational period evolution in some of these stars. And in fact, I would like to say that in some cases, for example, HD 1429 we have seen a faster evolution, a faster rotation, which is quite counterintuitive, because magnetic stars are supposed to be rotating slower, getting slower with time, not faster. So there is some physics lying there which we need to understand, and that is something which we need to probe in future. We have also seen that inner magnetosphere density is not a simple density. It is a very complicated density, and one needs to understand magnetic fields are not ideal dipolars. For the first time, we have seen the upper cutoff in ECME, which means the frequency at which electron resonance conditions cease to exist. We have not yet seen the lower cutoff, but there is a possibility that we may be seeing some plasma emission signatures at lower frequency, which is also likely to be coherent, but we need to study it more detail. And other thing is that we have proposed this, we have given the community this 3D propagation effect model, which can be used in ECME and try to understand various physical conditions. Where is this field headed to? We have to still understand that what causes ECME in some stars and not majority of the stars. Is it the fast rotation? Is because so far all the ECME has been seen in fast rotators. So we have now started a survey of slow rotators, and we have I think 3 or 4 stars in which we are looking for ECME on these slow rotators. We also are trying to see, is it the magnetic, is there a particular morphology of the magnetic field which prefers ECME or not? We are carrying out the wideband properties of these ECME star is important. Our work, what we are looking forward is to understand more on the magnetic O-type stars radio emission, because they are the ones which are progenitors of heavy mass black holes, and we need to understand these stars. So far we have seen only 2 radio emission, and they have shown very, very different kind of radio emission. So ION is working on this magnetic O-star radio emission and trying to understand that. We are also studying the stars, some of the magnetic stars, some which are very strong merger candidates, and some stars which are not the merger candidates. We are also exploring the radio emission properties with respect to the binarity. And so far, epsilon UP is the only system where the both stars are magnetic, and ION will be studying this system also to understand the binarity and magnetic field of the stars. And we are planning to understand the aspects of metallicity, and we will be probing some of the Magellan Cloud magnetic massive stars and see what kind of radio emissions coming from there. What is next? I think this is an ideal time to study this, because there are many polarization surveys going on in the recent time. MWA has had a 200 megahertz polarization survey where one of the ECME candidate was discovered. Possum survey with ASCAP is taking place. There are dedicated circular polarization survey taking place with ASCAP. So, and it is a very important science goal with SKA. So magnetism in massive star is, it's a very important field, and it is heading in the right direction. It is a very happening field right now. And I think with this, I will end my talk and take any questions. Thank you so much.
Thank you so much, Poonam, for an excellent talk, giving us a glimpse into the stellar evolution of hot stars and the role which the magnetic fields play and their manifestations and the puzzles which remain. And it's fantastic to see the systematic, detailed, and also pioneering survey of hot stars, and the way your group is trying to understand the clues from the CME emissions to understand and build a more realistic description of the magnetospheres of these stars. Okay. Thank you so much. Once again, we can raise our hands for questions. I am afraid I'm going to be allowing only one question in the interest of time. Okay, I don't see any hands raised. In which case, let me thank Poonam on behalf of all of us, and then move on to the next talk, which is the first of the two ASI Zubin Kembhavi awardees, which is going to be given by the first of the two Zubin Kembhavi awardees. Yeah. This is by Vivek Monteiro, and it is titled Universalizing the Universe with Daytime Astronomy and People's Science Movement. So I invite Vivek to please set up. You are a co-host, you have the privileges to unmute yourself. And maybe to avoid getting ourselves delayed further, I'll give you a warning, Vivek, when you're 25 minutes into your talk. Yeah, we can see your screen.
Can you hear me?
Yes, we can hear you. We can see your screen.
You can see me also, right?
Yes.
Let me begin by thanking, on behalf of the Nagalaxmi group, which is a number of organizations, on whose behalf I am accepting this award, and who have been very much a part, an integral part of the work that is going to be described in this talk. On their behalf, I thank the ASI for giving us this opportunity to share some ideas with you. I will begin by paying homage to the memory of Comrade Pansare, Govind Pansare, who who lost his life 5 years today. He was a frontline promoter of rationalist thinking and spoke a language that common people would understand. I also pay homage to Giordano Bruno, who 421 years on the 17th of February also lost his life. As you know, though Bruno lost his life, but he did not lose the battle. And that was won on the terms for which he was working for. And perhaps Bruno should be also remembered as the harbinger of a new age of scientific thinking. We often say that that age begins with Galileo, but let me say that perhaps Bruno is who preceded Galileo by some years, and who did not compromise, is the true harbinger of this age of rational scientific thinking. Of course, the relationship or the astronomy and public outreach have gone hand in hand right from the outset, very ancient times. And I must mention Anaxagoras, who 200 years before Eratosthenes got the right answer. He was the mentor of Socrates, Anaxagoras, and he obtained the same answer as Eratosthenes at 6,500 kilometers to a different question. He was looking at the question of how far is the sun. And in this book, which is a book by George Gamow, very nice little book, A Star Called the Sun, this calculation is described. The math is correct, the data was correct, it was the same data that Eratosthenes used. But Anaxagoras did not know that the Earth is round. And on one assumption, which he had no way of knowing probably at that time, which was wrong, he assumed the Earth was flat, and he arrived at the answer for the distance of the sun as 6,500 kilometers. When you put in the right premise, which is that the Earth is round, you get this right answer for the radius of the Earth. Anaxagoras was also a publicist. He was asked to stop, was prosecuted for blasphemy, and finally exiled from Athens. So as we see, not only is the connection between astronomy and public outreach very old, very ancient, but from ancient times, the public outreach also has been something of a hazardous occupation. The title of my talk today, Universalizing the Universe, was proposed in the IYA 2009 by Dr. Sabyasachi Chatterjee, who is currently the chairperson of the All India People Science Network and a trustee of Nagalaxmi. It means reaching out to everybody. It is a very ambitious concept. I seek your permission to talk about this concept in the context of India. Of course, we know that astronomy is a global exercise, perhaps not only in all countries of the world today, but perhaps in many worlds in all parts of the universe. And I will talk about India because in India, universalization has a specific focus. I'll describe that in a couple of minutes. What do we mean by universalization? I pay homage here also to Professor Sawyer, from whom Nagalaxmi takes inspiration for its work. And this is how he talks about universalization of mathematics. He says that the ability to think mathematically would have to be taken for granted as much as the ability to read a newspaper is at present. Such a change will seem fantastic to many people. So would universal literacy have seemed absurd a few centuries ago. To enter a new stage of history is always difficult. So reaching out to everybody. In India, this has taken the form of a legal mandate because of Article 21A in our Constitution, which was followed by the Right to Education Act 2009, in which universalization of education of good quality was made a fundamental right of every young Indian citizen. The word good quality has entered law, good quality elementary education. And after RTA 2009, mere access to education or mere universal enrollment is no longer sufficient. Now it has to be universalization of good quality education, which includes, of course, good quality science education. And what is good quality education is defined in the National Curriculum Framework 2005, which is also notified under the same RTE Act, and therefore has also become part of Indian law. NCF defines good quality education very strongly. It says that equality of opportunity is not sufficient. Good quality education has to deliver equality of outcomes. Equality of outcomes. And it further goes on to say that good quality education is defined as that which overcomes the inequality into which children are born. Very, very strong and robust definition of good quality education in terms of equality. I might also point out here that the NCF 2005 was drafted under the chairmanship of Professor Yashpal, also one of our kind. And it had the contribution of many scientists and science educators, like Professor Arvind Kumar, who was director of Homi Bhabha Center of Science Education at the time, Dr. Anil Saggopal, Professor Ramanujam from mathematician from Math Science in Madras, Professor Sailesh Shirali, Professor Krishna Kumar, and many others. Another aspect of the universalization, which has specific importance and focus in India, is the people science movement. Now here, public outreach is perceived as not just an activity, but a people's movement. And the credit for proposing this, and not only just proposing it, but actually trying to implement it, definitely goes to the Kerala Shastra Sahitya Parishad, which began as an organization to promote understanding of science in the mother tongue, but went on to become a mass organization with tens of thousands of members. And in 1978, they put forward the concept of a people's science movement before the whole country in a conference which was held in Kerala in that year. That concept of a people's science movement resulted in organizations to take the movement throughout the country. The All India People's Science Network is a network of organizations in every state. There is Vigyan Prasar, which is also a science promotion organization operating throughout the country. And Navnirmiti, whose work I'm going to talk about ahead, and the various other organizations who are part of the Navnirmiti group, which is the Trust, the Learning Foundation, the Equality Foundation, and also EduGeni from the Northeast. Navnirmiti is a part of the All India People's Science Network. Now let me talk about the growth of and the work of Navnirmiti. It began with a total solar eclipse campaign of 1995, which three organizations, Vidyan Sangatna, the Comet Media Foundation, and some mass organizations, trade union organizations, women's organizations, and All India People's Science Network, came together to conduct a national campaign for observing the solar eclipse. We designed and produced mass-produced solar filters, which were tested very scientifically in the spectrophotometer at TIFR, and which were manufactured by hand in Lax. And from that entire exercise, we learned a number of things. One is that we don't have to be an NGO. We can be an SRO, that is a self-reliant organization. We don't have to depend on foreign funding or any single project for our work. We can be very firmly dedicated to promoting the values of the Indian Constitution, which are very strong and very robust. And we could focus on our main objective, which is that of universalization, which is now a law, but it has yet to come into practice. And implementing it in practice on the scale that is mandated is not a trivial problem. And so Navnimriti began to work on the issue of math and science education, universalization of math and science education. For our self-reliance, of course, we learned from the episode of the solar filters that if you combine cutting-edge R&D with the organizational skills of individuals and the skills that are there in the unorganized sector, one can produce some very interesting tools for mass education. After the solar filter, the VLFL lens was another innovation. As you know, the size of the diameter of the image depends on the focal length of the lens. So you can get larger images if you increase the focal length of the lens. So we developed a 10-meter focal length lens, which gave us an image of the sun, approximately 10 centimeters across, which you can clearly see sunspots if they are there. In another campaign, the TOV, Transit of Venus 2004, that was when Navnimriti team developed the ball mirror solar projector, where if you project over 30 meters, you can get an image of the sun, which is around 30 centimeters in diameter. And there also we were able to see sunspots. That is the kind of resolution that you can get with a very simple mirror. TOV was also the time when we encountered Jeremiah Horrocks. If the credit for measuring the radius of the Earth has to be shared between Eratosthenes and Anaxagoras, because Anaxagoras got the right answer, so surely he deserves some of the credit. Jeremiah Horrocks got a very reasonable estimate, and had he made a slightly different assumption to the one that he made, of course, what he did was he looked at the Rudolphine tables of Kepler. He didn't believe them, so he did his own observations, made corrections to those tables, all at a very young age, and then decided that there was going to be this transit which is visible in 1639, which Kepler had missed. He not only predicted the date, but also the time. He observed it, and he measured the size of Venus. I'll show you. This is the diagram from his own diagram, which he drew at the time. This is the photograph from the 1882 transit of Venus. These happen every century and after 8 years. And this is a photograph of the last transit of Venus, 2004. Here, if you use Venus as a gauge with a certain assumption, unfortunately, Horrocks made an assumption which was very reasonable, but which was about 30% off. Had he made a different assumption, had he assumed that Venus, being a planet like the Earth, is the same size as the Earth, has roughly the same diameter as the Earth, he would have gotten an answer which would have been correct to 5%. And getting a right answer, of course, is rewarded by history. He surely would have gone down in history as the person who first measured the astronomical unit. All this is described in a booklet that we produced at the time, Measuring the Universe with a String and a Stone, which basically repeats the work done by Horrocks, but putting this assumption. And with this, children in any school with school mathematics can actually measure the astronomical unit. At that time, 100 years back, more than 100 years back, the work of Chintamani Raghunathachari, the first fellow of the Royal Society from an Indian, also needs to be highlighted. He wrote popular tracts which were translated into 6 Indian languages: Tamil, Kannada, Sanskrit, and Urdu. And this is a copy of the book where he also brings together not just the astronomy, but the public outreach in a very, very interesting way. The next campaign, which was the IYA 2009, that led to the development of some new interesting tools like the geosynchron, which is actually an Earth which is parallel, put in a position so that its axis is parallel to the Earth's axis. It's also called the rectified globe. And on this, children can learn a lot about many things about geography and seasons, astronomy. They can understand this is actually the way the Earth would look from a geosynchronous satellite if you were looking at it from that distance. In IYA 2009, we also developed what we call a sun dual. This sun dial is known to, this design is known where the gnomon is the rod and the scale is the disk. But what is not so well known is that if you interchange and if you look at the scale as being the gnomon, the circle as being the gnomon, and the rod as being the scale, if you do a dual transformation, then actually this is not only a clock, but it's also a calendar. The clock, that is time of day, is told by the longitudinal motion of the shadow, and the disk casts a shadow on the rod. That is stationary throughout the day. That moves latitudinally along with the calendar, and that is really a calendar. So these designs and the duality of the gnomon scale was also something very interesting which came out of the IYA 2009 experience. A handbook of daytime astronomy was produced at that time in many languages, and it was distributed throughout the country. And at that time also we found out that these activities can be done by students in schools anywhere in the country, whether in rural schools, in Adivasi schools, in elite schools. Everywhere children were able to make their own equipment, self-constructed equipment, and they use them widely. In the last solar eclipse, 21st of June this last year, this ball solar mirror was used by students in many schools, but it was a COVID time of pandemic. And students can also make their own telescope. Fairly good quality lenses can be made available at a not very high cost. The rest all locally available materials. And with that, children can project the sun, can observe sunspots, can observe transit of Venus. Of course, now it's going to be many years before that is possible. But very interesting experiments can be done with self-constructed equipment. One of the interesting activities which was conducted during IYA 2009 was to hold science fairs which were of the students, by the students, and for the students. And this was done successfully in a number of schools. This is a science fair going on at a school in Mumbai, Oberoi, the ABG school. From that experience also came out what is known as the nano solar system. I'll not describe this in detail. I'm sure many of you know what it is. Basically, it is the solar system which is scaled down by a factor of 10 to the power of 9. So what we see there in the slide at position number 3 from the left is the Earth. Position number 2 is Venus. Number 1 is Mercury. And the large, the other ones are Jupiter, Saturn, and Uranus and Neptune. And of course, there's very interesting mathematics which can be discussed as to how is it that such a small moon can eclipse such a large sun. The sun is not shown there. Actually, it's the size of a human being on the scale of, we are seeing that you can see it in the background. How can a small moon, which is even smaller than Mercury, how can it eclipse such a large sun? So we get into a discussion about very interesting mathematics discussion about when do two spheres appear to be the same size. Smartphone photography also, can show why two spheres on the left appear to be the same size on the right. And then from there we can go on to actually simulate many astronomical phenomena like the eclipse using the nanomode and an artificial sun, and also the real sun and a pinhole. So this resulted in another toolkit for organizing a Suryotsav in every school. It was also produced in many languages all over India and distributed through the All India People's Science Network. Now let me come to the final part of my talk today. It is about why self-reliance is important in the kind of work that we are doing. Well, today, scientific temper and rational thinking are facing some fairly serious challenges. Universalization is also facing a rather serious challenge because in the new education policy 2020, there seems to be a retreat from the commitment to universalization. Instead of equality of outcomes, what is now being talked about is equality of access. But the earlier and the RT Act 2009 went far beyond access to talk about outcomes. Another challenge is from the field of pseudoscience in the field of education and elsewhere. I will not talk about these details, but we are aware about what has happened even in Indian science congresses and what is happening with the curriculum in some parts of the country. Now, asking questions about these phenomena is something which we all feel the need to do, but even asking questions is sometimes discouraged and even penalized. And this is because there has been a pseudoscientific fringe always in many countries, it's always there. But when it's mainstreamed with the backing of big corporate money and corporate media, that's when it becomes much more challenging. And along with that, we know that there's a distorted concept of nationalism, which is amplified by the same media, and in which somehow it is a paradigm is trying to be promoted that asking questions is being, anti-national or anti-Indian. And therefore, it's very important for us to come back to our constitution and assert that, in fact, asking questions, which is a part of scientific temper, is our patriotic duty. Our constitution, perhaps, is the only constitution in the world which has scientific temper explicitly mentioned in its articles. I do not know of any other constitution in any other part of the world. That's why I said I will restrict my talk to what we can do in India. Here we have a legal mandate. We have a constitutional mandate for scientific temper. And as we all know, asking questions, asking the important questions is a very important part of scientific temper. And when we are asking questions, that is actually our duty, because as per our constitution, this is one of the fundamental duties of every Indian citizen: develop the scientific temper, humanism, and a spirit of inquiry and reform. Think scientifically and act scientifically is the slogan of an organization like Vigyan Prasar. So asking the necessary questions uncompromisingly, as we know, is a very ancient tradition in science, not only in Anaxagoras, but even in our parts, even in India. But it's not ancient. Now it is a modern responsibility, and it is an important role for the science movement in our country today. So the science movement and the All India People's Science Network has responded to this, and Navnimriti has been an important part of this. we produced a booklet called Ask Why, which shows how the scientific method can be used to universalize scientific temper. Now, it's not just scientific temper, but universalization of scientific temper, which is the legal mandate. And here, there are some interesting experiments, which include some experiments from astronomy, as to how children can themselves, through the method of science, through doing scientific experiments, learn to distinguish between bogus and what is something which is credible. August 20th has now been accepted by many organizations, including the All India Science Network, to be observed as a National Scientific Temper Day in the country, on August 20th being the death anniversary of Dr. Narendra Dabholkar, who also fell to domestic terrorism in 2013. And Dr. Dabholkar was a frontliner in the promotion of scientific temper. There's a wonderful paper written by him, Professor Nagalaxmi, and two others, about exposing astrology, throwing a challenge to the astrologers. This, by the way, is something that was done by Horrocks. It was done in a very gentle way, by our own Raghunathachari. Dr. Dabholkar, Professor Nadekar, and two others have written this very interesting paper on giving a scientific challenge to astrologers, which they could not answer. And he has also given some wonderful lectures in Marathi, which I have translated to, which I have translated into English, and now they have been translated into all the Indian languages. National Scientific Temper Day is now being observed on a very wide scale all through the country through AIPSN and organizations, which is actually playing an important democratic role in the country. Science, of course, needs democracy because it's itself a very democratic activity. Everybody has the right to question. Everybody is expected to question. No authority which is above questioning. So science needs democracy. My last point is, and our last point as Navdamriti, is that democracy also needs scientific temper. And when we strengthen scientific temper in society, we're actually strengthening democracy. And we have a role, the science movement and organizations dedicated to promoting scientific temper have a big role to play in defending and extending the democratic spaces which through public outreach of science, we can do this as scientists, we can do this as science communicators, and as citizens. So building a people science movement as part of public outreach is a very important objective in today's times. The All India People Science Network, along with the NSTD, National Scientific Temper Day, it has also taken up another campaign called SDHD, Sabka Desh, Hamara Desh. So the people science movement and universalizing the universe is very much a part of the larger democratic movement in our country. And I would like to use this occasion to invite everybody here to become an active part of the people science movement. We have a lot of work to do ahead in the days to come. I would like to conclude by thanking Zubin, Kembhavi, the Kembhavi family, Rajiv and Sasmita, Ajit and Asha for honoring us here today. And also, I would like to thank all my colleagues in the Navdamriti group, because this work would not have been possible without their very active and very integral contributions. So this is really a collective activity. And I would like to thank once again the Astronomical Society of India for giving us this opportunity to share these ideas with you. Thank you very much.
Thank you so much, Vivek, for not just a very interesting journey through the ages for the various milestones in Indian science outreach, but also the larger perspective in which this work lives and the larger perspective towards which Navnirmiti is working. Some of the toolkits produced by you and your organization, POEC, the Public Outreach and Education Committee of the ASI uses regularly, the Suryotsav and the Daytime Astronomy toolbooks. And thanks also for highlighting the challenges we face in modern times. Yeah. Reminding us of our constitutional duty to promote scientific temper. Okay, just one question. If please raise your hand if you wish. There's one from Indulekha. Yeah, you should be able to unmute yourself, Indulekha. Yeah.
I just wanted to ask, what do you think of fighting superstition by pointing out the logic behind them? Like, for example, don't go out during eclipses. Like, children are very curious. They might gape at the sun, because it is gape-attable when there is an eclipse. So these superstitions started at times when there were no newspapers, no schools, no TV, no etc., etc. So a logic which may not be necessary now might be operating. One can cite a few examples for this behind superstition. So I think that the logic that might work is an opinion which I have. Another question is, did you think of introducing the mathematics of at what speed should you walk to make the moon stop walking with us?
What was the second question? What was the second question?
The moon walks with us when we walk, or the sun or the stars. So at what speed should you walk to make it stop walking with us? Thank you. Thank you for a wonderful talk.
Yeah, thank you, Indika. Yes, I think the total solar eclipse or even the partial solar eclipse campaigns are a wonderful opportunity to combat superstition. And simple logic of just coming out and taking a look, taking a glimpse of the eclipse, that act itself, is worth 1,000 words of explanation of how the eclipse occurs. Of course, how the eclipse occurs is something which is very interesting for school students, but getting school students out in large numbers, it's not just the uneducated. Even a large number of very educated people are still more afraid of coming out during eclipses. So the superstition is something which is very prevalent even in the middle class. And the mathematics of moon walks, why the moon walks with us, about parallax. Yes, this is all very interesting mathematics, which is really amenable to school geometry and experiments which we can do parallax, in the classroom, school done. Yes, daytime astronomy is a wonderful introduction to mathematical physics, which can be initiated at a very young age, even in class 4 and class 5. I'll just conclude this comment here.
Thank you so much, Vivek. Thanks on behalf of the whole of ASI for this wonderful talk. And now we move on to the last talk in this session, which is by Samir Dhurde, who's sharing the ASI Zubin Kembhavi Award with Vivek. Samir, you were a co-host. I request you to please set up. And I'll remind you maybe 25 minutes into your talk. My apologies for running late, but I just couldn't get myself to stop or interrupt our speakers or push them to be faster.
Sure. No worries about that. Thank you very much, Divya, for arranging this. And I know there was a shortage of time, but you've managed to give enough time for both of us to present. I will just share my slides right now.
We don't see them yet.
No?
Yep. It's appearing, but not yet. Yes, we see them.
Yeah. So, well, thank you very much for having me here to give a short talk about the work that we do here. And I've chosen today to present the outreach done at my home institute, which is the Inter-University Center for Astronomy and Astrophysics, IUCAA, as it is popularly known as. Also, the fact that IUCAA has one of the earliest and I would say one of the best outreach programs, a particular department led, which I happen to be heading right now, and one of the best teams for outreach in astronomy. So I thought maybe rather than just showcase the efforts, we'll also talk about what could be done in future of organized outreach. Now, I of course also congratulate my co-awardee Vivek for his great efforts. And I remember that I personally was inspired by, to come into astronomy by several people in my life, several people who took out time and effort to actually communicate astronomy to school children, which I was also at one time, and particularly in the 90s. And there were like solar eclipses happening in, I think 1996, 98, there were solar eclipses. And I saw Professor Jayan Narlikar on screen, on Doordarshan. What better inspiration than seeing a scientist also being popular and coming down to your level and explaining things. And also showing how much they enjoy, being a scientist, being an astronomer. So that was a great push towards me coming to Pune, joining IUCAA at a much later time, and getting into what is organized outreach through the outreach program. So the primary aims, again, set down by the pioneers of this, like Professor Jayan Narlikar. Their vision was that IUCAA should have a separate mandate to to reach out to the public and students and the next generation, basically. And we have to inculcate science interest in students, particularly the underprivileged ones, because they are not easily reachable. And we have to make extra efforts to reach them and also to encourage them, to give them access to various resources. Of course, from this whole pool of students that we reach, we could find some motivated, talented children, and we should encourage them to take up science research. And of course, in general, as we always say, we have to keep the public informed to keep their support for our subject. So, astronomy has to be promoted because it is a very vital subject, and it has played a great role in mankind coming to this level of civilization, I think. I mean, things, simple concepts like time, etc., have come from observations of astronomical cycles. So, so although it has been a very important subject, very good observations have gone into leading us to the space age today, but it's losing its value today. So therefore, it also has to be promoted, and the public has to understand the importance of it. NGOs like Navnirmiti and of course organized efforts like IUCAA have been collaborating together to reach this goal. So a short timeline, of course, quickly to go through how it evolved. So we started right at the beginning, right from the beginning of IUCAA, even I think when we didn't have a building, we were still doing outreach in the 1990s with Professor Narlikar, starting things like the second Saturday lectures programs, the regular visits to IUCAA campus, and sky watching shows, other important programs. And this was being done with students and teachers in and around Pune around that time. We also were reaching a lot of amateur astronomers, which is still one of our big target audiences. In 1995, around 1995, I would say, we started with national campaigns and big events where we started to aim bigger. We started to reach larger audiences and also tie up with organizations which would help us focus our attention to more general public across the nation. And we also started communicating with the media. We started communicating with in various unique ways, like radio shows and TV shows, etc., which was very uncommon for a science research institute to get into even then. So in 2014, we had an event, which is the inauguration of our science center, which is called Muktangan Vidyan Shodhika. Now, IUCAA's SciPOP program, Science Popularization Program, is not just limited to astronomy, but we also foray into science education, science popularization. And so it's a comprehensive effort in getting children interested in science and then showing the value of astronomy in understanding several things in science. So the Muktangan Vidyan Shodhika is host to a team right now, including where I'm sitting right now. This place, this small science center, sees visits from hundreds of children every week. Every week, I would stress. In the normal times, we are right now missing all of them, and we are heading towards the National Science Day, which gives us about 10,000 visitors every year. But this science center is the prime hub of all these activities for outreach right now. It was built with the kind donation from Pooja Deshpande and with the vision of Professor Nandita. So today, as I said, we continue our work and are connecting our experts, not just in IUCAA, but across the community of astronomers to the thousands of students and public every year in unique ways. Now, quickly to show you some of the regular programs. These are some things which we have been doing for 3 decades now. So, and they're being emulated many places. And these are lectures, open days, special programs during summers, including summer camps, observation programs for school students, competitions, etc. happen here. We have, in fact, in parallel right now, we have a competition for school students happening on our YouTube channel right now with some 150 students participating in it online. We have public visits, sky shows, and a very unique program, which is the telescope making program, initiated by Professor Rana and Arvind Paranspe, who was my senior here, which has a very popular appeal in which several telescopes types have been designed, which can be made with very low cost or easily available material. So and these are good quality achromatic lenses which are used, or you could grind your own mirror at our workshop and have your own reflecting telescope. It's very popular and is now being taken up across the country in collaborations with organizations like Vigyan Prasad. So yes, we do move out of our campus, and our Science Toys project has been very important to us. And this has also given us a lot of reach, because we were lucky to have Professor Mr. Arvind Gupta with us. He is a Padma Shri awardee from 2 years back, and the Science Toys and what we also call the Space Toys project has had a huge reach across the country. And that also got us into online outreach. And I'm talking about 2005, when people were just thinking about websites. We had a website which was visited by thousands and hundreds of thousands of people across that decade, previous decade. Now we have YouTube channel with several languages, resources in several languages, etc. We have astronomy-focused workshops, teacher trainings, and very unique things like space toys, which are basically used by teachers to ease the concepts that they teach in schools. So our team studies all these things and then makes these particular resources for them to use and adapt. We have mobile planetaria here in IUCAA, and again, as I said, for the last 1.5 decades, I have personally been going out with mobile planetaria, and at many places I've seen these mobile planetaria not mobile, but we actually hire a car, go out and set it up in rural environments. We teach teachers we train teachers how to use these, and they can use them themselves. So it's not just about giving something, but also enabling teachers and science communicators. So this becomes part of our rural outreach, which is also extensive. And right now we started this program, I think Arvind Paranspe and the Public Outreach Committee at that time decided that we need to have a specific program for the IUCAA Giravli Observatory region. And we started there, but now it's gone very broad and we reach so many more people across the state. Of course, because of the pandemic last year, there has been a stress on online outreach, and we have been doing a lot of programs. We are there on these channels that you can see on this slide here. But this is not new for us. We have had all these things since 2013-14, right? And our lectures have been live for the last half a decade. Every event is shown live. But it's now that people are noticing the channel. So yes, it's good. And we had all these special events online last year. And we started our first event, which was actually for LIGO India. But we started our first event right 8 days into the pandemic lockdown. So within a week, we knew the value of outreach online, and we had started a lecture series already. The highlight was and the annular solar eclipse program, which has a viewership of around 2 lakh right now, that video. And it was in collaboration with the ASI's Public Outreach and Education Committee. It was a huge success with so many astronomers joining in, reaching out to the people and talking about everything, including superstitions and the importance of solar eclipses and solar observations, and Aditya mission, which is also great. So the people got a great overview of the event, but extra information from our astronomers in 8 languages. So all of them made an effort to explain this in several languages as well. So all these things we have achieved over the years. And of course, let pictures speak louder. You can see there's a lot of numbers, but there's also a lot of joy and satisfaction in doing all these activities with students, general public, and with amateur astronomers. So a few numbers just to show that, yes, we reached some thousands. This is just now data from 1 year, from 2019. Last year doesn't count because the numbers may be more, in fact, since there have been a lot of outreach on the internet. So we go on from here. Now I come to this aspect, and since there's very little time, the importance and the value of this program, which is called IUCAA SciPOP, is that the program is organized in a way, and we are very goal-oriented. So over the years, we have had surveys done amongst teachers, amongst students, amongst the people around us, amongst amateur astronomers, and we base our work on these kinds of surveys. Now that makes our efforts very effective, both in terms of how much time we spend on it, and also in terms of how we manage to give quality of work in outreach. Now, you may have an event, and if it's well planned, all of you know, it's not just I'm not just talking about events. It could be any research, any project, any kind of program that you have. So all these require a lot of planning, and this is something which IUCAA makes sure that we do. And all our events are planned well in time and implemented with proper pipeline of a sequence of planning steps that are charted out. We ensure that there is quality. We look at competition because we are in a government institute right now. We're supported by the government, and it's always easy to say that, okay, we are doing something and just do something. But there is also the concern about quality and accuracy of what we say. So there are regular checks on what we are doing. We also check out competition across the world, and we see what are the tools being used for outreach, what are the media being used, what is the future of future which will become popular with people, and so can we reach that? So these are things we keep in our mind, and therefore our effort becomes a little bit more effective. That's when I say that if organized outreach can actually reach a lot of people. It also allows our publicity to percolate. And these days we have WhatsApp, which is an excellent tool. But in the pre-WhatsApp days, we had to send out posters, printed posters, and then they had to go to colleges and people had to read them, and they had to reach other institutes. So, organized work actually gives you enough time for publicity as well. This is very important because you might do a great show, but there are hardly any viewers. There's hardly any audience. So it kind of defeats the purpose. So it's very important for publicity to happen in time and in an organized way. Also, it should be widely done in collaborations. Of course, I have to say that if you are working in a project mode, if we have a project rather than just an event, the completion of the project is ensured, because if it's an extended project for a year or so, the team may lose track, they may get distracted into something important. If you have a pipeline and if you have a plan, you'll ensure that the project is completed. It also leaves us with the provision for a feedback and follow-up with the people who were targeted. Because this is another thing I've noticed in Indian outreach, that we lack feedback on what is being done. There are, of course, good contributors who do all these things, but many organizations and many individuals who go out and do outreach on their own somehow lack this feature of getting feedback. And therefore, their quality improvement doesn't happen so rapidly as it should. The follow-up and feedback is very important. Also, we very often miss out on documentation of what we do. And that also comes as a part of organized working, because you will therefore have some part of your work set out for documenting what you're doing. And documenting is something which ensures that your efforts would later also be seen by people. Okay, not just for appreciation, but if it's something like a textbook or a good video or something, people will see it because you have documented and put it up at a good and visible place. So that's the importance of being organized. I would also show that as there are many people here from various institutes which have interest in outreach, I would like to say that yes, this is a very privileged position. And with that come the expectations of people. So they are looking up to our institute, our organization, to tell us about what we do. Okay, so astronomers have to talk about astronomy. It's one of the most popular and most curiosity generating subjects. The Mars mission has flooded our social media with questions. So yeah, I mean, there are expectations from people. But then the privilege, that's also an advantage that there are more people looking up to you, so there are more people you can deliver to. And you have easy access to subject matter experts. Right now, I work with, our team works with the ASI and various institutes, and there are various departments also which are there. And then we collaborate with various other NGOs in transferring our resource material or events outwards. We also help them reach their resources outwards. So that's a great privilege to have. And we are allowed time and a good work environment to study several things like STEM concepts, education standards, and 21st century skills. These are important to know because a team has to be up to date, and it also has to show the value of their work. So just like Vivek has highlighted, that the teams have to work with all these things in mind. They have to be relevant. Their work has to be relevant and also popular and exciting and inspiring. So in an institute, these things are available to outreach personnel. Of course, with the institute's name, etc., you have ease in getting funders and partners. So I think to those who are into outreach right now or who are thinking of getting into outreach, I think these are some things to cash in on. And if you have an organized effort, then it's easier to showcase it. It's also easier to make use of all these privileged things that we have to bring it, to combine it with that organized plan and have fruitful work. Now, I will just highlight some of the essential skills of our EPO team here at IUCAA. And this is something I think is, in general, should be true for an APO team at any institute. And we should have focus on education, communication, website development, and development of visual material like infographics, images, and videos. These are extremely important points, and I'm very happy that through IUCAA and with the support of all the people at IUCAA, we've been able to get together this team. We have education experts, we have some people who are very expert in putting out messages on social media, and they make posts and they know all the technology behind it. We also have website developers. We have an internship program here. So other than the regular employees or the contract employees, we have an internship program where students at BSc, MSc level who have interest in outreach in astronomy can join us for a little while and work on a focus project. So they could, for example, illustrate something for us, make slides, presentations, or infographics, which sometimes are much faster to communicate than just a chalk talk or a speaking talk like this. Videos are the latest and the most engrossing medium, and we have a team, in fact, which works on videos. There's a good collection of video recording equipment, there's a video editing equipment. So all these things are provided, and the EPO team also has skills in this. So this is my suggestion for every EPO team to at least have. Coming to the future, the next gen Indian projects are there, and they're they're almost in the process now. And all of these science missions, projects, astronomy, missions, they will require education, public outreach, and communications, and also some workforce development. I think ASI is doing a great job with the workshops which just happened in the last 2 days, and the POEC is also doing the rest of it. And similarly, I think these kind of organizations should take up this kind of planning on these topics of workforce development, education, and communication to the people. Now, I cannot end without showing you the team. And this is maybe with 1 or 2 people missing. This is the team giving support to the Vigyan Samagam exhibition, right? Which was one of the, what I'm proposing has already been done once in the Vigyan Samagam traveling exhibition, which was hosted in 4 major cities. And so there it is, the team of people who have all these skills, and they reached, this is the Mumbai event. So I would stress that with projects like these coming up, we should be looking at collaborative efforts. So all these, rather than having individual efforts, could also have some collaborative things and devise new ways to reach students and the public. I believe that outreach is not something we do only to inform and explain our work to people, but it inspires the next generation's achievements. Okay, and there are several examples. I think there are some in the participants list also, and I won't be modest about it. So they are there, and we all are here because that spark was inspired somewhere by some person doing outreach. So there's no need to emphasize the importance of it. Only I say that there should be collaborations and organized efforts to get the widest reach possible. We should not contain, ourselves. We should not just, limit ourselves, but try to reach the most number of people with this kind of organized efforts. So, thank you. I have been very fortunate to have the support of IUCAA and the IUCAA SciPOP team. And therefore, I would like to accept this award from the Astronomical Society of India on behalf of the team and all the members who have been part of this effort for the past few decades. Thank you very much. And of course, I have to thank the ASI for taking up these efforts, especially through POEC, but also through this special award. I'm thankful to Professor Kembhavi and Dr. Asha Kembhavi for this great award that they have set up. This, I think, will inspire the next generation of science communicators. So this is an extremely important award because the kind of visibility it can give to a science communicator is very important. And so this will go a long way in, I think, making very strong science communicating organizations or individuals in the future. So with this, with these words, I would like to end my talk. Thank you very much.
Thank you so much, Samir. Thanks a lot for a sort of comprehensive overview of the IUCAA SciPOP bouquet of offerings, right? All the way from regular lectures and open days to telescope making and the mobile planetarium. And also for the sort of behind the scenes view on the detailed planning which goes on to execute a successful science popularization program and the necessity of sort of follow-up and feedback to sustain a program for the long term. Thanks also for emphasizing the need for collaborative efforts as we go on into this era of many mega projects and the need to build our scientific community in terms of numbers and interest as we go forward. Okay, thank you so much. And thanks also for actually sticking to time. Yeah. Okay. So one question, please go ahead and raise your hand and I will unmute you. Okay, Nandita. Nandita, I think you're already a co-host, so you're welcome to ask.
Yes. Thanks and congratulations, Samir. Through your talk, you mentioned about the online internet which was used for public outreach last year and about the mobile planetaria, etc. So with these modern tools and much better approaches, what do you think traditional planetaria in which you have to invest a lot, what is the future of those, and is there a thinking about along those lines to exploit the best out of them?
Oh, definitely. I think, and since you're talking about planetaria, I'm not such a great expert, and there are many in the outreach committee of the ASI. But regarding the mobile planetaria, it is something which can take the sky to a remote place. Okay, of course, which also has the natural sky, but this aids the way you can talk about it quickly and bring a lot of things. But
that is cheap. That is cheaper. So I was just asking what happens to the traditional planetarium.
I'm coming to that. Yeah. So basically, this cannot replace the traditional planetarium. Traditional as in the bigger planetaria, because they have the experience there is completely different. Also, I think the International Planetarium Society is working on making these more modern, and therefore now these planetaria can integrate data, actual astronomical data into their shows, and there are visualizations, etc., being planned, which cannot be done in a mobile planetarium, I think, currently. So this integration and this, there are also virtual environments which are coming inside the planetaria. In big cities, etc. So I think there are some efforts happening from the International Planetarium Society, which will increase the value of planetaria as a presenter of, or a connection between actual astronomers and the people. While mobile ones will still run pre-recorded shows, I think.
Thank you.
Since there is only one more question, Indulekha, you can go ahead and unmute yourself and ask. Indulekha, you should be able to unmute yourself.
Yeah, I can do it. Thanks for a nice talk. You were talking about feedback. I was just wondering whether the IUCAA SciPOP puts up a sample feedback form in their site, just so that people can use it.
Yes. All our events are followed up with a online form these days. And of course, when the teachers are here, they fill out some forms and we look through them. If you want an example, I could email it to you. Just drop me a mail.
Okay, great. Yeah, thank you so much. So it's time for me to thank all the various people who presented their talks in this session, and my congratulations to all the ASI awardees and also the ones who weren't here to present their talks, right? So thank you so much. Thanks for an invigorating session and a nice start to the ASI. Let me just say before I announce the end of this lecture that the next session starts at 1:30 We'll have 3 parallel sessions on stars, ISM and galaxy, instrumentation and techniques, and extragalactic astronomy. All of you should already have the links to that. I request the speakers to log in 15 minutes early so that they can try out any issues, just in case there are any issues with connectivity and sharing of presentations and so on. So thank you so much, everybody. With this, I bring this session to a close. My thanks once again to the presenters and the awardees and to the audience. Goodbye.